Hello everyone and welcome to the first session as part of the EN workshop, which is about the power system principles for non-electrical engineers. Could you please confirm you can hear me okay and you have got the webinar slide visible? Excellent. So what I'm going to do tonight, actually my time of course, is basically give you a general concept of the power systems with a special focus on the switching devices for the transformers and the protection systems and the power quality. All right. I'm not going to be too fast, and at the same time I'm not going to be too slow because I've got a lot of slides actually to cover. So the first thing is, okay, so this course about electricity. I know that there are some people like electrical engineers among you, but my assumption is that I'm just going to assume that whatever your knowledge and background is, it is not mainly focused on the power engineering, say at an engineering level. So I'm just starting from a very, very basic question saying, what is electricity in effect? We have got a lot of electrical appliances all around us, like TV, like the hair dryers, like the electric bulb, like the washing machine, like the iron or something, all right? So what is electricity? We need electricity to run all these devices. Electricity has got a number of different important parameters by itself. One of them is the electric current. Who in this class can tell me quickly other parameters, important parameters that you can find within electricity? Could you type please, what are other important parameters that you understand? Maria, perfect. Voltage is another one. So we have got current and voltage, and I can still find other parameters. Okay, amperage, Alec, is the same as current. Okay, amperage is the same as current. So voltage and current, and yes, power factor, and what is the combination of current and voltage? What is the multiplication of voltage and current? Resistance is okay. So Paul, what is the unit of measurement? All right. So the parameter itself is power. Is that right? Excellent. So we have got power, we have got voltage, we have got current, we have got resistance. There is something more. What is the thing in your, okay, so if I ask you what is power, you would say power is the thing that does the job, okay? For example, you have got lights, you have got the motion, you have got the machine running or something like that, you have got the TV on, you have got the radio on, so this is power, okay? So if I ask you what is power during a period of time, what is the thing that your electricity bill is based on? Every month you are not paying for power, you are paying for something else. Your electric bill is not based, I'm talking about residential, okay? It's not based on power. It is based on, okay, that kilowatt hour is the unit of measurement for, that kilowatt hour you are referring to is the unit of measurement for, starting with the letter E, my dear friends, it is not electricity, nope. It is energy, okay? So the issue is the electric or electrical energy, E, all right? So we have got power, we have got energy, voltage, current, and resistor and power factor. Okay, question for the class is this. If I'm just going to, so don't worry about I'm not turning over the pages or something like that. I will do it quickly. But all I want from you guys in here is just to come into a very proactive contribution into the class activities so that I make sure that we are on the same page. All right, so we have got the same understanding about the electricity. If I want you to make a comparison, okay, between an electric circuit, okay, and the hydraulic circuit, so that you have got, for example, water, okay, in there. So let's say you have got a tank of water that has been installed at a height of h. Okay, so you have got that tank installed at a height, okay, and you have got water installed in it. That tank by itself has got a valve. So if you like, you can drain water out of the tank. All right. My question is this. If you want to compare this electric current with another feature of that hydraulic system, okay, of that system, that water or something like that, this electric current is similar to what? Electric circuit, electric current in an electric circuit is similar to, Jeremy, the flow of water flow. Okay, so excellent. So that is similar to water flow. In your opinion, this electric voltage is similar to what in that system? You need something so that you have got a current, you have got a flow of water. So that has to do with that valve, isn't it? Is that right? Okay, so gravity is correct, amount of water is correct, but that, my dear friends, that gravity and amount of water together produce something so that as soon as you open the valve, the water will be running out of the valve, and the name is pressure, Alec. Excellent. Okay, so we have got pressure as opposed to voltage. But either this system or that system, this pressure and voltage has got another name. Again, starting with the letter P. And who knows that? This pressure and voltage, another name that we can do, you can use for that in English is starting with PO. So, nope, it's not power. It's not power. So think about the dam. You have got power behind the dam. Yes, Hector and Maria, potential. Okay. So you need to have potential energy. Okay. Potential energy is the thing that you, let's say, need to have for that. Okay. So basically, we have got the, let's say, the definition for current. We have got a definition for voltage. Now, in your opinion, this electric resistance that you are referring to, it is similar to what in that system? I give you one hint. In this electric circuit, tell me, what is the thing by which you can carry that flow of electric current? First, focus on the electric circuit. What is the thing that you have got to carry the electric circuit, the electric current from one place to another? Excellent. Conductor. Correct. That conductor could be line conductor, could be cable conductor. Okay, I'm asking, this cable or line conductor is similar to what in that system? In the other system. In here, you have got cables. Okay, so that's pipe. So once again, I'm asking, this electric resistance is similar to what? Anyone knows? It has to do with that pipe. Okay? It has to do with that pipe and also that valve. Size, what do you mean by size? What exactly do you mean by size? Okay, so it goes back to the diameter, okay? The diameter of that pipe. So if the pipe is, for example, very wide, in that case, you can carry a lot of flow. Similarly, if you have got your wire, your cable, your conductor, very big size, in that case, you can have a lot of current in that conductor or pipe. At the same time, you understand that when the current is very high, the voltage or potential or pressure is very low. right? When you make it thin, in that case, the pipe is now thin. The wire is thin, okay? So it can carry very low amounts of current or flow, but at the same time, the potential, the pressure, the force, the voltage is very high. That's how this electric system works. However, rather than water, in here we have got other particles. We have got electrons. We have got protons. So that's the movement of these electrons that we refer to as the current, or the flow of electrons, rather than having the water. So when I want to get a resemblance between the two systems, I can say that I've got a water tank. Same amount of water can be stored in the tank. However, I can put it at a height of 1 meter, or I can put it at a height of 10 meters. So what's the difference? The difference is the potential. The difference is the potential energy, pretty much similar to what you have got behind the dam. It depends how big, how tall is your dam. Therefore, this water container tank at a height of 1 meter can be similar to a battery you have got with 1 volt potential. The other one can be similar to a battery with a potential or voltage of 10 volts. So that's the meaning of electricity. That is where we're coming from. So as long as you do not have any path between these protons and electrons, there is no current. Therefore, it is similar to that valve. As long as you have not opened that valve, there is no flow of water. Once you open the valve, it can be fully open or it can be half open. So that is the first bit of resistance that we put in there. And then once it's in the pipe, again, depending on the size of the pipe, the diameter of the pipe, the thickness of the pipe, there could be other resistances, even friction, for example. Okay, so this is similar to an electric resistance that you can have in an electric circuit, or something like this. Okay, so that one is referring to that resistance that you have got. So finally, you have got a load. The purpose of everything is that you are causing this electric current to flow for a purpose. In this case, for example, the purpose is to light a lamp. For your case, in that water system, the purpose could be to fill in a tank, to wash something, anything, okay? So you need to have an end user. You need to have a load. So all in all, I'm talking about discharging electrons. So we have got a positive pole and we have got a negative pole at all the time. The issue is to make a way just for the discharge of electric current and energy. Sometimes it is desired. It is controlled. It is within our control. Sometimes it is not desired. Like this lightning. So lightning is not desired. It is absolutely out of our control, and this is not what we want. So that's a very quick and huge and massive release of energy. The exchange of electrons and protons between the two surfaces, which in this case is the surface of the ground and the clouds. However, the controlled ones are what we have got for batteries, what we have got for generators, what we have got for capacitor banks. So we have got the controlled ones and we have got the uncontrolled ones. So what is happening in lightning is that that's a massive, huge electrical discharge between the molecules of the cloud and the ground. But there are some circumstances in here. Not at all the time lightning occurs in all places and at all heights. No. It depends on the geographical situation. It depends on the distances of the clouds from the ground level. It depends on the formation and configuration of those electrical charges of electrons and protons in the cloud and on the surface of the ground. It's more like a magnet. If by chance, right at that time when you have got a lot of rain, heavy raining, just by chance, if, for example, in a spot, if you have got lots and lots and lots of electrons accumulated in one place for any reason, and right at that time, if you have got positive charges above it in the cloud, as long as this distance is too much, nothing's going to happen. You're going to have just rain. But the clouds are getting closer and closer and closer to the ground. All of a sudden, there is a spark. There is a big arc. There is the release of energy between the cloud and the earth. And this is what we call the lightning. My question for the class is, in your opinion, what is the reason for that spark? Why there is a spark like that? Why is that? So in other words, I rephrase it. Why is that at a particular distance, this spark doesn't occur, but as soon as that distance becomes less than something, that spark occurs? So there is something in between those positive and negative charges. And what is it? What is between this positive and negative that prevents resistance? What do you mean resistance? I'm talking about this example. This is not electric circuitry. This is lightning. What kind of resistance? The resistance is correct. I'm asking Alec and others, what kind of resistance is there in between so that you and I are safely walking in the street? It's raining very hard or something, and we are still safe, unless we are very, very unlucky and right at that spot there is a lightning and we may be killed or something, right? So what kind of resistance is in between? So physically, do you agree between that positive and negative charges there is air, isn't it? It is not vacuum, of course, right? You have got air. So that air has got a feature so that it will prevent these electrical charges to meet each other and build up a current unless they are very, very, very close to each other. And that feature's name is, it has got a name. It has got a name. If you have noticed the battery, you have got a positive pole, you have got a negative pole. There is something in between. Think about your car. Think about your car. What do you have inside the battery? You have got a number of cells. What do you pour in the cells in your car? Water? Battery. Do you pour water? Distilled water, and there is something else. There is something else. Acid. Yes, there is acid. So do you know the name of that acid in English? Starting with the letter D. Anything like that that comes in between and can control the flow of current between positive and negative charges. So you need to have a controller in between. So God has given us by nature that controller. One of those controllers is air. The name is dielectric. Okay, so you need to have a dielectric in between so that that dielectric naturally will control the flow of current. Okay, that dielectric has got a feature, and that feature is called dielectric strength. Therefore, naturally, we have got air. That air has got a dielectric strength. That's why you just walk freely, and we have got a lot of cables, we have got a lot of transmission lines or something. You just walk, you just drive, and you are safe. Nothing happens because you have got air. And that air has got dielectric strength, and that air prevents that live conductor to damage, to injure, to kill you. That's what it is. But if you get very, very close to bus bars, to live compartments, to transformer bushings, to, I don't know, panels or something, yes, you could be electrocuted because that dielectric strength is compromised. This is what is happening in here. Okay, so that's the meaning of electric discharge, that when it goes on out of the control, in that case you have got an unwanted spark or electric arc. But as I said, it is a parameter of many different things. Like it is a parameter of humidity. It is a parameter of the distance between the cloud and the air. It is the parameter of the kind of things that you have got on the surface of the ground that creates that kind of electric charges. If, for example, the electric charges in the cloud, they are positive at the bottom part, and the electric charges on the ground are also positive, it's more like the magnets. They are not attracting each other. As a result of that, there is no lightning strike. The bad thing is that one side you have got positive and the other side you have got negative, and things get out of control. So in here, again, you can see that even the temperature is another parameter. How much temperature do you have? Because condensation is also important. That's how rain is created in the cloud. However, sometimes this flow of charges are funny, like what you have got for a static charge. It's a dry day. You and I are wearing rubber shoes. We are walking on a carpet. We meet each other. We are going to greet each other. We just shake hands. And after that, poof, you may have experienced that so many times. Okay? Again, you are trying to touch the door handle. You're going to get out of the room. That door handle is metal. You just touch it and poof, again, another discharge happens in there. You just try to comb your hair. Again, you can see that your hair becomes like that. Even you can attract some small tiny particles like paper with that comb. So it means that it's more like it's been magnetized or something. It can attract tiny pieces. So again, in here you have got the static charges. Sometimes these static charges are not just funny, okay? So it just gives you a giggle or something. Sometimes, no, it can chill people. Like, for example, the static charges that can be accumulated on a metallic frame of a panel, of a cubicle, or whatever. You touch it innocently and boom, you are electrocuted. So we must be very careful. It is not something to ignore. We must be very, very careful of that. So these are examples of the static charges. Therefore, if someone asks what are the limitations of this static charge, we say in thunderstorm clouds, the static charges can build up to millions of volts, which is of course very dangerous. It cannot move and is limited to what? To only small distances. So one of the limitations is the distance between the cloud and the surface of the ground. Static charge can cause damage to electronic equipment. The static charge can also cause uncomfortable shocks. Especially if this kind of sparks are close to flammable gases, they can cause fire, big fire. like the pump stations or whatever. So we have got these things already in place. So as I said, we have got controlled and uncontrolled flow of current. The controlled ones, like we have got in batteries. So as you can see in here, we have got an electrolyte in between. That electrolyte in between, that can create, as I said, dielectric strength. And at the same time, it is responsible, as you can see in between, responsible for controlling of the flow of current, electrons, protons, so that you can keep this battery in a store. Other than that, as soon as you produce it, it is discharged, finish. All the load is gone. So, as I said, for this electric charge to flow, you need to have a load, something like an electric bulb, something like, for example, a resistor, something like a motor, something like a transformer. So you need to have a load so that you are going to make a link between the positive and the negative poles. So this is the meaning of battery that was first introduced by an Italian scientist called Alessandro Volta in 1800. And in the honor of his name, now we have got the word volt, which is the electric potential. Therefore, the main components of a battery are the positive pole or electrode, the negative pole or electrode, and the electrolyte that comes in between and creates current. These batteries have got different forms. These days we have got rechargeable batteries, non-rechargeable batteries, we have got the alkaline batteries, we have got dry type batteries, we have got acid batteries, we have got electrochemical batteries, chemical batteries, many different forms of batteries. We have got car batteries, we have got motorcycle batteries, we have got different types, therefore different electrolytes, therefore different charging and discharging at different volts. 6-volt battery, 3 volts battery, 9 volts battery, 12-volt battery, 24-volt battery. So combination to a battery is a battery charger. If you don't have a battery charger, in that case, after a while, that load will totally use up the electric energy inside the battery and the battery is gone. However, some of the batteries are chargeable, some of the batteries are not chargeable. So as you can see in here, we have got different types of batteries available in the market that you can use. Even for fun, just I advise you do it in your kitchen next time. You just take one lemon, big one, or just a number of them, put them in series, and push a number of nails in them, and just connect them together by means of wire, and put an electric bulb, a small one. You can light it up by lemons, depending on how many lemons you have got and how sour they have got, because it all depends on the acid inside the lemons that can work like electrolyte for you. Therefore, as I said, in order for you to be able to make an electric current, you need to have the positive and the negative poles, and at the same time you need to have a load and wire in between so that you can have a current of electrons and protons. That wire can be copper, it can be aluminium, or it can be anything else. I have already explained these to you, so you understand the meaning of voltage. You understand when we say 20 volts, 10 volts, what's the meaning of that? You understand the meaning of force or pressure or potential. You understand the role of the valve to control the flow of current. This valve, again, is similar to that resistor, but the resistor is not just the valve, but also it has to do with the diameter of the pipe, or in electricity, it has to do with the size of the conductor. So we have got voltage, we have got current, we have got the flow. Also, I talked to you regarding the height. I talked to you regarding the diameter of the pipe, which is a means of controlling the flow. It can be the flow of water, or it can be the flow of electrons. Therefore, in electricity, we measure that potential of force or pressure or whatever by means of volts. We measure the flow of electrons by means of amperes, again in the honor of the name of another scientist. Interesting thing is that a lot of them are German ones, like this Mr. Ohms, okay? And again, the electric resistance is measured in ohms. So resistance is a feature that slows down the flow of electrons, and resistance causes an opposition to the flow of electricity. Who in this class knows the equation or the formula for resistance, electric resistance? If someone asks you, hey, could you give me some very, very simple equation that comes from physics, high school? Ohm's law is one of them. Excellent. So Ohm's law is V equals Ri. Okay. So it shows that this R and I and V are connected like this. Okay. Ohm's law. If someone asks you this, just focus on this R. What is the equation for this R? This R is depending, it depends on what? Forget about V and I, R by itself. When I say the resistance of this wire is 10 ohms, 20 ohms, it depends on what? I have not connected that to any battery. So there is no voltage, there is no current, okay? So it's not a matter of Ohm's law. I'm not talking about the, Hector, material. What do you mean by material? I'm just talking about that wire. Forget about volt and current. It's not been connected to any supply. I'm just talking about that wire. The resistance of that wire depends on, excellent Hector, conductivity, and it is not just conductivity. Conductivity. Okay, temperature is a tuning factor, fine-tuning factor, but what are other things? Do you think that the resistance of a 1 meter wire is the same as the resistance of a 10 meter wire? Do you think? Is that the same? So length, correct. Length is another one. So we have got the wire, the conductor, conductivity, and the length. And do you think the resistance of a thick wire is the same as the resistance of a thin wire? So there must be another thing in between. Excellent, Hector. Cross-sectional area. Okay. So all in all, I can say that you can write it down for yourself if you like, or you can listen to this recording later on or watch it. So it is rho times L divided by A. So this rho is the conductivity. L is the length of that wire, and A is the cross-sectional area. So if it is, for example, this L is in terms of millimeter, this A should be millimeter squared. Okay, and then this will be ohms. Okay, so you understand that R is directly related to L and reversely related to A, and again directly related to rho, which is the conductivity, resistivity. So the higher the resistivity, the higher the resistance. The more the length, the more the resistance. The more the sectional area, the less the resistance. This is what we have discussed so far. Now, we say that the effect of resistance is heat, is the loss of the the thermal energy. So sometimes this heat is good. We intentionally make this heat. Sometimes this heat is bad. Who in this class can tell me one example of having heat as a good thing? So who can give me an example when I intentionally increase the resistance so that I'm getting heat? Yes, like oven, like heater in industry. Can you give me an example in industry? From mine, for example, what is the thing we have got? Of course, it's not a simple electrical heater or something. Water heater is correct. And have you ever heard of electric furnaces? Okay, they have got electric furnaces where you have got big rocks, big rocks. Okay, so you would like to heat them up, you would like to melt them. Okay, so rather than having a big fire, for example, out of burning something, you can use electric energy to make that big heat so that you can melt down something. All right, but sometimes it is bad. Like, for example, if you have got a motor and if it is heated up, you've got a transformer, it is heated up. You've got a generator, it is heated up. That's bad. That can kill the equipment. So sometimes this heat as a result of high resistance is good. Sometimes it is bad. Now that you have understood the meaning of the current and voltage, I'm telling you that in very general terms, they have got AC currents and DC currents. Direct current or alternating current. So again, I remind you of that positive and negative. If the location of that positive and negative is the same, constant. So at all the time, for example, you can say that where I'm standing, at all the time on my left I've got the positive and on my right I've got the negative. So at all the time the direction of the current is the same from your right to your left. That is DC. But sometimes intentionally we make it in a way in our generators so that the locations of this positive and negative is just changing regularly. In that case, that's an alternating current or AC. The reason why they're doing that, it is not a subject of this presentation in here because it will ask me actually to go into the very detail of generators or something, but it's just telling you that there are very good reasons behind that. We can get a lot of more power out of AC circuits rather than DC circuits, but at the same time, we can get a lot of good controls over this DC circuit. So all I'm saying is that both are available. LV, MV, and HV. They are all available within the market, okay? So we can get very high voltage DC, low voltage DC, medium voltage DC, high voltage AC, low voltage AC, medium voltage AC. They are both available, okay? So it's very simple for DC, as you can see in here. So it's not a matter of time, okay? So if this is the time, for example, XS, it's not a matter of time. And all the time, you are having a constant voltage. However, when it goes into AC, you can see that those positive and negative charges are just changing the location regularly, repeatedly. That repetition, as you can see in here, who can tell me this? According to your understanding, what is the name of these repetitions? So it is just this wave shape is repeating itself. What is the name of these repetitions? And Paul, you are fantastic, mate. Okay, so the name is frequency. Okay, Hector, excellent. So do you agree that these repetitions can be repeated in a period of time? Okay, so in a set period of time, I can have these many repetitions, or within the same period of time, I can have these many repetitions. So the top one is what we call the low frequency. The bottom part is what we call the high frequency. But this time period is what we call the period. So as you can see in here, T and F, or period and F, frequency are reversed. So in other words, I can say T equals 1 divided by F, or F equals 1 divided by T. Another question for the class is this. If someone asks you in the UK, when you say one period, one cycle, that one cycle means how much second or millisecond? Do you have an answer to that? Do you know how much is it? Do you know how to calculate that in the UK? If someone asks you one cycle, excellent. One cycle means 1 divided by 50. Okay, 1 divided by 50. 1 divided by 50 means how much? 1 divided by 50 means how much second? I'm talking about T. I'm not talking about F. I'm talking about T. So one cycle, which is one period T, is 1 divided by 50, okay, or 2 divided by 100. Or it is 0.02 seconds, not 0.2, 0.02 seconds. Okay, 0.02 seconds. You tell me how much millisecond is that? 0.02 second is how much millisecond. So you have to multiply by 1,000. Okay, excellent. So 20 milliseconds, okay, is what we have got. So 1 divided by 50, my dear friends, yes, is this. Is that correct or not? Is this it or not? First of all, I'm telling you this is second. One cycle is this much second. Is this correct or not? 1 divided by 50. Does that make 0.02 or not? Yes? So it is not 0.2, it is not 2. Now this is second, or when you multiply by 1,000, you get 20 milliseconds. So this is what you have got in the UK. Could you tell me how much is one cycle in the United States? Who knows that? Okay, could you simplify, Maria? 1 divided by 60 means how much? How much second, how much millisecond it is in the United States? 20 milliseconds for the UK, and come on, 1 divided by 60 is 10 milliseconds. Have you got a calculator? Aha, Hector, correct. That's it. So that's second. All right. Hector, is that correct to say 16 millisecond or not? Is that correct to say that 0.016 that you are saying is excellent? 16.67 millisecond is the correct answer. Excellent. So all I'm saying is let's say the similarities between this frequency and the period. So they are saying the same thing. This is high frequency, or HF. This is LF, low frequency. Okay, so what happens is that from this end, I can say that when you talk about this three-phase, when you think about this AC circuits, okay, it can be divided into single phase and three phase. Okay, who in this class can tell me what is the benefit of a three-phase system as opposed to single phase? Who can tell me that? You have got, for example, not more voltage, Paul. It's not a matter of voltage. You have got air conditioning system in your home. It can be single phase. It can be three phase. At all the time, you just connected that to 220 volts. So it's not a matter of voltage. Okay? It's not a matter of voltage. Alec, you are close, but it's not a matter of... Okay, so the load... It's not a benefit. More load is not benefit. The thing that supplies the load is more important. So in other words, more power. So 3 times more power you get out of that. So all I'm saying is that as long as your load in home Okay, it's something like lights or refrigerator or TV or I don't know, your personal computer or something like that. It's not a big load. So you can handle that with a single phase power. However, if you have got big, for example, powerful air conditioning system in your home, in that case the single phase system would not be sufficient. So you need to have a three-phase system actually to come in between. So again, we have got three-phase system as opposed to single phase. So again, the way how it will be single phase or three phase, it goes back to the design of your generator. It all goes back to the split of the loads. So normally the power company gives you three phase. What you can see in your street, what you can see in your alley, what you can see in your neighborhood, it is all three phase, three phase, three phase. However, you can see that how they have given your home that power, they have just given you one wire, and that is your one, that is just single phase, because you are a residential load, you are not an industrial load, you are not a shopping complex, you are not I don't know, a cinema, you are not an office, you are not a factory, you're just a home. So single phase is enough. So they give you phase A, they give your neighbor phase B, they give another neighbor of yours phase C, and again A, B, C, and again A, B, C. So this is how they will distribute the three phases in your street, in your alley. However, the important thing about this three-phase system is that you have to distribute that as much as you can equally. If you don't distribute that equally, what will happen is that you will have an unbalanced system. And when you have got an unbalanced system, in that case, that's going to be very bad, because you have got unwanted or leakage currents. You will have the overheat of the machines. You will have damage to your, let's say, household appliances or something. Okay, so when we are dealing with three-phase and single-phase, we have to be very, very careful about that. So when you think about the electric power, basically this electric power is a multiplication of V and I basically together. Okay, so this is the let's say the way it works. Just hang on a second, please. I just opened something for myself because I can't see that page from the webinar. Just hang on a sec. I'll quickly get back. Okay. All right. So as you can see, the electric power is basically measured in watts. So this is basically what we discussed. So it's a multiplication of V and I together. And what happens is that this electric power and yes, so it has got two basically components, two important components. One of them is the real power and another one is the reactive power. So one of them is P and another one is Q. Together, this P and Q make together S. Okay, so as you can see in here, we have got the triangle of power. This S is the apparent power, P is the real power, and Q is the reactive power. Now, I've got a very simple question for the class, and the question is this. When you pay for your power bill, okay, in that case, is it based on P, or is it based on Q, or is it based on S? You tell me. Are you paying for P or Q or S? Just as a matter of curiosity. See, you don't have the same idea. All right. So I asked this question in another way. The transformer, right? Let's assume you have got a zone substation, and in that zone substation, you have got a transformer. That transformer is feeding power into your home. In your opinion, that transformer, the nameplate of that transformer, is that in terms of S or P or Q? The rating of the transformer is S or P or Q? Okay, I give you one hint. That rating of the transformer is normally given as MVA or kVA. The rating of the transformer is normally MVA or kVA, and that MVA and kVA, for your information, is the unit of measurement for S. Therefore, the power company has already paid for S. In other words, that power company has already paid for both P and Q. However, when they give that power to your home, you are paying for P, and that W energy is based on P. So what's the benefit of Q? The benefit of Q is that it is working like a facilitator. It is working like a catalyst. It is working like a motorway, a freeway, a highway that you have got. You need to have a pathway for those electrons and protons to move around. Now, if you have a look at that triangle, you can see that there is an angle between P and S. Do you see that? That angle is the angle of, are you on, can you see the triangle or not? As far as I can see, you are on page 32. You cannot see that? You should be able to see that. Is that correct to say that the thing that you are seeing is just P and Q? Is that correct to see that you are seeing? Okay, so what about this page? Oh, okay, now I understand, sorry. Can you see the triangle? Can you see the triangle now? Yes. So can you see the angle between the P and S? Can you see the angle between the P and S? Okay, so that angle is the angle phi, okay? Cosine of that phi is the power factor. Now you understand the meaning of power factor. So when I say, okay, so put it this way, what is the meaning of having everyone, first of all, everyone agrees that normally in the business, we would like to have high power factor, is that correct? For example, we would like to have 90% power factor, 95% power factor, okay? If you have got pen and paper, please write it down. Write down power factor equals P divided by S. P divided by S, according to what you can see in the triangle, because power factor is cosine that angle, cosine phi. Now, could you tell me what is the meaning of a high power factor? Why do you want it to be high? Why do you want to have a high power factor? No. That's not because of balanced load. Do you agree that if power factor is 1, 100% unity, do you agree P equals S? Is that right? If power factor is 100% or 1 or unity, do you agree P equals S? Is that right? Excellent, Jeremy, excellent. It means that the utility is telling you that I gave you S. I gave you the whole thing. If your power factor is 100%, it means that you have converted all that S into P. So you have used the maximum power, and at the same time you paid me for that maximum power because your bill is based on P. However, if your power factor is low, it means that your Q consumption is very high while you are not paying to the power company for that Q. In that case, the power company will tell you, hey, you know, mate, what's the matter here? The thing is that you are wasting my energy. I have already paid a lot of money for this transformer. I am giving you S, which is a combination of P and Q. You are wasting my Q. You are wasting the highway. This highway is for 1,000 cars. However, you have put only 100 cars in this highway. You are wasting my investment. If I knew from the beginning that you're going to drive only 100 cars, I would never ever build such a big highway in here. You have wasted my investment. That's why you will have to pay fine to the power company for having a low power factor. And who in this class knows in what way you can correct your power factor for the power company so that you are not punished, you are not charged, you are not receiving any fine? Who can say a very, very common way that we use in industry? What is the thing that we, yes, Hector, capacitors. We have got cap banks, we have got capacitors to be connected to our loads. And you can write down for yourself that when we have got capacitors in place, what happens is that they will inject Q to the system, so that the power company is giving you P and Q. You are using P and you are using Q. At the same time, you have got capacitors connected to your load. And again, they will not inject P. P is gone. P, you have used it. But they will inject Q. So they will make a balance so that the power company is happy. It's more like I give you 10 pounds from and plus $5. You use the 10 pounds and you will return the $5 to me. That's the deal. If you do not return that $5 to me, I will charge you. The pound has gone, okay? Pound sterling is gone. You have used it, you have spent it, okay? I'm not dealing with that because you will receive a bill for that. But I will just bill you just in terms of pounds, not dollars. So you have to return the dollar, whatever, because that was a package from the beginning. Can I say that in this class, everyone understands the meaning of power factor, the benefits of high power factor, why the power company charges and fines and whatever if your power factor is low, and why you need to have capacitor banks in your site to compensate and correct the power factor and Q. Are you happy with my explanation here? You understand the meaning of power factor, you understand the meaning of the triangle of power, you understand the relationship between S and P and Q. Or are you happy, or you need some more explanation? Because that's a very important thing. Hector is happy with that. What about others? All good. Okay, so how about for you, Alison and Carol? Are you happy with that? Alison and Carol are people from the UK, right? So happy, good. Okay. So guys, I'm just going to give you, because this is the end of presentation number 1, and the rest of the pages I'm pretty sure you can read for yourself, and I don't find you can find any problems with that. However, by all means, if you have got any issues, just send a request to the course coordinator and I'll be at your service. Okay, I'm just going to give you guys 5 minutes break, please. Okay, I'm gonna take these pages out of the Moodle and I'm just gonna upload another one. I'm just gonna give you 5 minutes if you want to have cup of coffee or something, and I'll be back in 5 minutes. Is that okay? Cool? Okay, excellent, guys. So I'm just going to give you 5 minutes and see you in 5. Excellent, perfect. Hello everyone, I'm back. So this is session 2, which is about the electrical measurement, transformers, isolators, fuses, and circuit breakers. So once again, you hear me okay, and you have got the webinar slide visible, correct? Okay. Have you got full energy actually to move forward and be a good companion, right? Everyone's full of energy, so I'm just going to ask again questions, right? Perfect. So basically, we already know a good understanding about the power systems. Now we are going to go into the measurement of that. We talked about voltage, current, power, energy, frequency, period, or something like that. Now we are going to measure. So the device that can measure the voltage is what we call the voltmeter. The device that can measure the current or ampere, this is what we call the ammeter or ampere meter. We also have got wattmeter, which is the power meter. Basically, we have got frequency meters. We have got power factor meters. These meters can be analog or they can be digital. But at all the time, they have got a positive lead, which is normally red, and they have got a negative lead wire, which is normally black. Okay, who in this class can tell me some of the advantages of having digital meters as opposed to analog meters? I'm pretty sure you have got something in your home, for example. You have got one of these meters at home. If you have got any problem with your fuse box, for example, if you have got any problems with something you can measure. So Jeremy says accuracy. Okay, accuracy is correct. As a result of that, Carol says readings are more accurate. Yes. So accuracy is one correct thing. Is that all? Is that just accuracy is the same thing? Is that the only thing, accuracy? Accurate reading. Okay, cool. So what happens is that, what do you mean, by the way, by a smaller measurement, Alec? Does that mean that we are limited to measuring smaller quantities? Oh, okay. So again, you are getting back to that matter of accuracy. Okay. Yeah, Maria, resolution. Excellent, excellent. This is perfect. And can I say digital meters are cheaper, in your opinion? I'm not so familiar with the market in the UK, but is that correct to say that if I want to get one of those small multimeters, digital ones from your market in London or something like that, okay, is that correct to say that relatively they are cheaper than analog ones? Okay, I think it's 1.99 pounds. Excellent. So you are very, very accurate, Alec. Okay, excellent. So on many occasions, even in here, on many occasions, these digital ones are cheaper. So I've got a very quick question, and the question is, even these days, when you go to a lot of sites, power stations, substations, industrial sites, still you can find a lot of analog meters, and don't think that they are, well, they are old meters and they have never been replaced. No, even new ones, you can find a lot of analog meters. So there must be some kind of benefits, and in your opinion, what kind of benefits are there? Are there any benefits or not, especially in industrial sites? So accuracy, yeah, just I give you something. When I ask you to read something by analog meter, okay, you and I are reading the same thing, huh? I would say, how much volt are you reading? You would say 3.65. For the same thing, I read, well, no. In my opinion, it is 3.67. You would say, hey, Beruz, maybe your eyes are suffering from stigmatism, or you are short-sighted or long-sighted or whatever. You can say that, because it is a matter of how you are reading that. That's why you guys are referring to accuracy, okay? Because when it goes into digital, when it shows 3.68, there is no matter, there is no dispute. 3.68, everyone understands what is 3.68, okay? Reading is reading, okay? That's why we say that's more accurate. However, there are some problems in here. Who knows one advantage of analog meter? Especially, let's assume you are an operator. You are sitting in a control room. All around you, you have got a lot of meters. Do you find any benefit? Okay, no battery, I accept that. Perfect, perfect. And again, in terms of your comfort, let's assume you are an operator. Do you find any comfort in reading the analog meters as opposed to digital meters? What do you mean true reading, Jeremy? Analog is true reading. Okay, so let's assume you are at a distance of 3 meters to the meter. If it is digital, whatever it is, okay, if I say what's happening, you have to go pretty much close to the panel to read that thing, especially if it's a message, if it is an alarm or something. However, if it is analog, if it even just by a glimpse, you can say that if the amount is high or low. You may not be able to read exactly from far away how much is that, but you can judge whether it is high or low, because you can see that needle, you can see that angle, you can see that, well, it shows something high or it is show something low. Even from far away, you can see that. But you cannot make such a judgment with digital. You have to get close to have exact reading what it shows. That's why even these days a lot of operators are more comfortable to work with analog meters rather than digital meters, depending on the application, depending on what is it to be measured, depending on whether you are in a hospital or you are in a power station or you are in an industrial site, whether it's a petrochemical industry, whether it's pharmaceutical industry, what? Depending on the application, some of the operators are more comfortable with analog, even if they know that there are a lot of advantages with digital. So the parameters we just covered in session 1, we are just going to measure voltage, current, power, which is a combination of real power, apparent power, reactive power, energy, watt hours, kilowatt hours, power factor, and frequency. And of course, we have got the harmonics. Who in this class, this is the subject of the last one that I'm going to say, session 4. Who knows the meaning of harmonics? What's the meaning of harmonics? Who knows that? When, well, so many times every day you hear about harmonics, and you hear these harmonics are bad, or we just want to prevent them, we just want to avoid them, we just want to eliminate harmonics or something. So we have already discussed the other things. Paul says more than one frequency. So we have got the base frequency of 50 hertz or 60 hertz, okay, and we have got multiples of that base or main frequency that are created by themselves. Okay, we are not creating. Who knows one of the things that can create harmonics, one of the causes of harmonics? What is the thing that can cause harmonics in your opinion? If someone asks you just a simple question in your work, you are not an electrical engineer, okay, agree. Even if you're a manager, you are someone from the admin or something, but even your colleague, they're saying there's, I don't know, someone from admin, they tell you about harmonics. They understand the meaning of harmonics, right? So what is the problem with this harmonics? Phase angle firing. Okay, so If that thing happens, if in addition to that 50 hertz, you have got 51 and 60 and 65 and 70 and all of that, and all these things go into your cable. You have already connected this cable to your TV. You have connected this cable to your refrigerator. You have connected this to your washing machine, to your computer, whatever. Rather than 50 hertz, you have got, so you have got interference. And what is the problem with that interference? You have got a mixture of different frequencies that are unwanted frequencies. And what is the consequence of that? What will happen to your load? What will happen to whatever you have been connected to this wire, to this cable? You know what? You have got, depending on what kind of load is that. If it is a TV, distortion in the image. If it is a radio, noise. Even again for TV, noise. If it is telephone, noise. If it is internet, noise. Sometimes breakage. The whole equipment is just burnt, like the fridge. Okay, dishwasher, burnt down as a result of harmonics. So we have to be able to eliminate all these things and also measure all these things. Therefore, you can see here we have got a combination of different sorts of, these days we call them multimeters, because they are not just limited to volt or amp or frequency or whatever, resistance. They can measure many different things. Voltage, current, resistance, power, frequency, harmonics, power factor. They can do a lot of things. They can be digital, they can be analog, they can be DC, they can be AC. At all the time, we connect the lead wire of red color to, for example, connection A, if it is measuring amp or current. And the common or black will go the other way. So again, we have got something like positive and negative. And the load or that measuring thing comes in between. Either it's a battery or whatever. So you can measure the current that goes through the battery, or you can measure the voltage of the battery. Put it this way. Imagine I've got an analog meter. Okay? I have got a 9-volt battery, as you can see in here. I connect the red to the positive pole of the battery, and I connect the black to the negative pole of the battery. That's an analog one, okay? So that's going to be something like this. So I'm sorry, hang on. Okay. I'm talking about this kind of thing. All right? I'm talking about this. That 25.18, right? In your opinion, if I reverse the polarity, if I connect black to positive and red to negative, what will happen? Analog. That's an analog one. If I reverse the polarity, in your opinion, what would happen? Nothing. Same reading, but there is a difference. The difference is you will have reverse deflection of the pointer. So rather than coming in here, it will go in here and tries actually to move this direction, because it is going to show you something like minus 25.18. This is one of the bad things about analog. But when it goes into digital, rather than doing all this, it simply add a minus sign in here. As easy as that, okay? It will put something like this in here, okay? So it will add a minus sign in here. So it will make it minus 25.18 or something, okay? So this is how it works. So we have got more comfortable reading with digital one. When it goes into very sensitive, for example, ammeters, we would prefer to call them galvanometers. So basically, the way it works is that, okay, we have got positive pole, we have got negative pole. We connect red to positive, we connect black to negative. But what is inside a galvanometer or ammeter or voltmeter is that it has got a coil. And it has got a permanent magnet, as you can see in here. See the permanent magnet, N and S, okay? And you have got a coil in between. And that coil's been connected to a needle or a pointer. On the normal situation, where you have connected nothing to this device, that coil, which is on the same shaft as the needle, is under the influence of the magnetic field of the permanent magnet. So there is no move. It is on the 0 point. So it is showing 0. 0 current, 0 volt, whatever it is, 0 resistance. However, when you connect those lead wires, it means that you are pushing some current into this coil. Who knows in this class what will happen when you push some current into this coil in here? What will happen in your opinion? Do you know what will happen? See this coil in between, huh? So I'm talking about this, right? In your opinion, if I push some current to this coil from this direction, what will happen? Ah, okay, so Alec, you're right, electromagnet, okay? This needle will move as a result of a second field. So we have got a magnetic field as a result of that magnet, and we have got an electromagnetic field, which is a temporary field, okay, as a result of that current that you are pushing into that coil. If that current, and as a result of that, the resultant electromagnetic field is strong enough to capture and conquer that permanent magnetic field of the magnet, in that case, the needle will start to move. And this is how you would calibrate this equipment. When you say, I have calibrated that, it means that you are adjusting the magnetic power of your magnet, or you are defining the number of turns of that coil, which has to do with the power of that electromagnetic field. Who knows the name of the English scientist who first introduced this theory to the world? And this theory is in the honor of his name so far for many, many years. That was a Mr. Who, starting with the letter F, who introduced this theory to the whole world. You know that? Who was the first person? Yes, Mr. Faraday was the person, and that Faraday said that if you have got a conductor, okay, and Frankenstein, Alec, are you joking, right? So that is so if you have got a conductor here, okay, and if you push a current through this conductor, there will be a magnetic field all around this. And that magnetic field, now, who can tell me this? Listen very, very carefully. I'm talking about the movement of the coil, isn't it, right? This electromagnetic field produces something, and that something is the thing that will cause the coil to move. And what is that? Starting with the so once again, I'm asking the question, if you've got my voice. I'm saying that electromagnetic field by itself cannot cause the needle and coil to rotate, to move. What is the thing that can really cause the coil or needle to move, which is the resultant of that electromagnetic field and is starting with the letter T? That is the thing that will cause this needle or coil to move. So the result of that electromagnetic field is something starting with the letter T. And that T thing is the thing, no, that is, what is the thing in your opinion that can make something to move? Is that tension? You need something to move, so you have to apply something. Torque, yes, Maria, you need to have torque, okay? So this is what causes this needle to move, okay? So it has to do with the magnetic field of NS and the magnetic field of that coil and the angle between, or sine alpha, and that sine alpha is the angle between the two fields. That will give you the torque that can make this needle to move. Therefore, as I have put it in here, my dear friends, torque is the thing that is the resultant of this magnetic field and can cause this needle to move. So we need to have torque. This torque has to do with the magnetic field of this NS and magnetic field of this coil, plus some kind of correction factors. Therefore, under the influence of this torque, this needle will start to move, will start to deflect. Now, if someone asks you, this torque is depending on what? Well, it depends on the magnetic field. The magnetic field is depending on what? That is depending on the current. And that's why, if you have got this scale and if you have got this pointer, if you are measuring a small current, the pointer, the needle is here. If you are measuring a big current, the pointer is here. Why? Because it has received more torque. It has received a stronger torque. It has received a stronger field. Okay? So this is the basic concept of that. Well, you can use this galvanometer to measure current. You can use this galvanometer to measure voltage. And as a result, you can use this galvanometer to measure ohms. Then, according to your coil, according to the number of turns of coil, you can have a range for your measurement. For example, you can set your ammeter, if you have used this galvanometer as an ammeter, to read something between 10 microamp to 10 milliamp, or between 10 milliamp to 100 milliamp, or between 100 milliamp to something, and so on and so forth. So you have got a selector key. When you change the selector key, you are changing the number of turns of that coil. As a result of that, the magnetic field will change. As a result of that, the torque will change. As a result of that, the force that is applied to that needle will change. And that will give the sensitivity of your equipment. If you have adjusted to something like 10 microamp to 10 milliamp, of course, you have set your equipment to behave very, very sensitive. If it is between 1 to 10 amp, well, the sensitivity is very low, but you are measuring very high currents. So all I'm saying is that if by mistake you have set your equipment to measure something between 10 microamp to 10 milliamp, and by mistake you just connect it to a source which can pass through your equipment something like 10 amp, in that case, bang, your meter is gone. All I'm saying is that you need to have a good judgment before you connect your metering device to the circuit. You have to understand approximately how much current I'm just going to measure. Approximately how much voltage am I going to measure? No problem about volts. If your judgment is wrong, you are not reading anything. So you just change the selector switch. But if you've got a battery, if you would say, well, it's a 9-volt battery, well, yeah. So this is this big battery, yeah, well, I would say maximum it will have half an amp. Okay, so I would set my device to 1 amp. So my expectation is that this needle will be deflected for half the scale. This is my expectation. Could be a little bit more, could be a little bit less. But if your judgment from the beginning is wrong, it is not in the order of 1 amp or something, half an amp. No, it's in the order of 7 amp. And all of a sudden, as soon as you connect, the needle will try to burst itself. So it is just putting pressure to the very end of the scale. Okay? You should be very, very lucky that you do not damage your equipment. If it's got a fuse or something like that, that will operate and the galvanometer stays healthy, but the fuse is gone. So these are the things to be very careful about. So I told you about the permanent magnet. I told you about the coil. I told you about the magnetic field around the coil. I told you about the angle of rotation, which can be 360 degrees. So this instrument is based on the movement of coil. Sometimes the coil itself will move. Sometimes the coil is constant, but let's say the connections will move, and as the result of that, the iron part will move, and the pointer will move. So therefore, you can understand that once the deflection is done, for example, if this pointer has already been deflected up to here, right? Now you disconnect the source to this meter, and as a result of that, your expectation is that this needle should be back to where it was. So how you can make sure it will do that? By means of a spring mechanism. So there must be a spring mechanism so that the needle again return to where it was. Therefore, based on what we have discussed, we can have DC meters, we can have AC meters. These moving coil meters are normally used for measuring DC currents and voltages at low power consumption. And they have got normally a shunt resistor. So what it says is that normally if you're going to measure, for example, this kind of things, it is showing, it is having a shunt resistor. Shunt means parallel, okay? So that it will pass the current through itself rather than pass the current through the load. And that equipment will use this current which goes through its shunt resistor to do that measurement for you, to create that torque and magnetic field and all that story that I told you. Or it can be a moving iron instrument, which is used basically for using AC currents and voltages. So it says in here, it shows it measures RMS value. Who in this class can tell me the meaning of RMS? RMS means how much. When I say, okay, how much voltage do you have in your home? You would say 220 volts. I would say 220 volts is the RMS value. Root mean square pole is correct, but do you know the equation? Do you know the equation for that? So just I give you this. Look carefully, please. Again, I tell you this. Look, this is the sinusoidal AC pattern. Okay? That we have got. It can be current, it can be voltage. So this is time. Just for simplicity, let's assume this is current. So this is I. All right? So it has got a maximum here. And it has got a minimum here. So this is I max or IM. And this is minus IM. Okay? Same thing applies to voltage. It can be V, it can be VM, and it can be minus VM. All I'm saying is that if someone tells you, okay, if this is IM, how much is IRMS? Remember that IRMS equals IM divided by square root 2. This is how it is. VRMS equals VM divided by square root 2. In industry, for some particular reasons, rather than referring to max, we're referring to RMS at all the time. So all these figures that you can see, 200, 400 or whatever in here, they are all RMS values. They are not max, but you can easily convert for yourself, okay? How much is the maximum voltage or maximum current? So we have got voltmeters, we have got ammeters, we have got power meters, energy meters. We have already talked about that. I said that they are normally measuring this kilowatt hour. So again, P is measured in terms of kilowatt or megawatt. Q is measured in terms of kilowatt and megawatt. Oops. And S is measured in terms of kVA and MVA. One more time, you are paying to the power company only this P. You are not paying Q. But if you are an industrial load, in that case, since your Q consumption is high, the power company will look at the triangle of power, S, P, and Q. So they will measure the angle between S and P to measure the power factor. Put it this way, if what they want, you know what they want? Okay, so normally this is it. So this is P, okay? This is P, and this is Q, and this is S, okay? You know what they want? They want your P to be as close as possible to S. They would like you to give something like this. Look, look, look. Again, this is a triangle, isn't it? Again, this is P, this is S, this is Q. Huh? Again, this is a triangle, I can say. But that Q thing is very, very little. You cannot make it 0. If you make it 0, in that case, sorry, the freeway is closed to the traffic. So you cannot totally make it 0. You need it for the flow of energy. And that's why the power company cannot ask you to make it 0. But they just close their eyes as long as your Q is something tolerable. If it goes beyond tolerance, in that case, no. They will come to your house and talk about your load. Hey, mate, what are the things you have connected to your system? I can read very large amounts of Q in here. Then all of a sudden they would say, okay, so this is a garage. Okay, so you have got big motors in here. So it's not just residential load. What is that? Okay, so you have got a workshop for yourself in here. You are doing some kind of mending things and repairing things or something. Okay, my understanding was that you are a residential load. Sorry, no. It's not working like that. Okay, so basically you have to pay for this thing. So again, Maria is saying audio's gone. Is that the same thing with others? My understanding is that everyone is hearing my voice. Is that right? Everyone is hearing? Yeah, okay. Maria, can you hear me, please? Maria, can you hear me? Well, it seems that so everyone is hearing me. Maria, can you hear me? Okay, so it seems that we don't have Maria here, right? Okay, so anyone else is hearing me? So my system is okay. At least. Okay. Maria, can I ask, where have you been connected to the system? Are you in the UK, Maria? Where are you based, Maria? Can I ask, where are you based? Are you in the UK, Maria? All right. Okay. So I just continue. So we have got different sorts of okay, so we have got different sorts of power meters in here. So we have got the standard meters, we have got off-peak meters, we have got prepayment meters. So all in all, we have got a tariff, okay, for our meters. So you have to pay for a combination of things in your meters, like the constant power and your variable, let's say, usage. Also these days we have got the smart meters. Can I say that in the UK, either Ireland or England or something, these smart meters are very popular these days? Do you have these smart meters in your homes or something, so that they can communicate with the power company? They will give you alert whether this is the right time or this is not the right time actually to I don't know, start your washing machine or something. Okay, so some of you have got in your home and some of them you've got it in your office or something. Okay, so these smart meters are just the new technology, advanced technology. So they are not only measuring the energy, but they are communicating with the power company and they are monitoring your, let's say, consumption of energy. Have you ever heard anything bad about these smart meters? For example, people complain to the power company that, hey, you know what, please do not install these smart meters in your home. Thank you very much. I'm quite happy with my conventional meters and I don't like to see the sight of these smart meters. Have you ever heard that someone complain about these smart meters, or for example say something bad about these smart meters? In your opinion, personally, do you think that the idea of having the smart meters, if we can afford the cost of that, saying either the power company is I don't know, willing to replace your old one with a smart one at no charge, or you just pay a contribution to that? Do you find any, if you just not think about the cost of that, anything like that, do you find any problems with this smart meter? So is that all good, right? So they just communicate or something, right? Okay. So for your information, some people here complain that these smart meters, right, since they are communicating with other places, it's more like a transmitter, receiver or something. So again, pretty much similar to what we have got that discussion of electromagnetic field. So they are saying that these are more like something like an antenna. So you have already put it in there, so they are transmitting, receiving. So at all the time, the people in the house, they are exposed to that radiation of signals or something. So some people are not happy with that. So again, I have no comment, okay, so because it's not been proved or something, but some people argue like that. But technically speaking, these smart meters are all good. And as long as you can afford the cost of that, that will be fantastic if you have got it in there. So I talked about the digital multimeters as opposed to analog multimeters. I talked about the DC as opposed to AC. I talked about the reverse deflection. I talked about the comfort of digital meters as opposed to analog meters, the way you just connect the, let's say, the red and blue and red and black. To measure the resistance, again, same thing happens. You have to connect the two ends of it to the resistor. You have to select the appropriate range. Okay, so that was for the measurement. What about transformers? Again, we discussed it. Transformers, I talked about the Faraday law. I talked about the magnetic field around the conductor. Now, there was another British or English scientist who just completed what was said by Mr. Faraday. He again agreed that if you pass a current through a conductor, an electromagnetic field will be around it, but he not only accepted that, but also showed the direction of the magnetic field, the red ones. Who was that person? Starting with the letter F again. So he said that if you get this wire in your, for example, right hand, so that your thumb is showing the direction of the current, the other fingers will show the direction of the magnetic field all around it, as you can see in here. So your thumb is showing this direction, and your other fingers are showing this red one. Any idea? Who said this right-hand rule? Who was the person who said this? So that if you get this conductor in your hand, your thumb will show the direction of the current, and the other fingers will show the direction of the field. Okay, so that was a Mr. Fleming. Okay, so that's the right-hand rule of Fleming that we understand. So we have got the Faraday's law of induction, as I said. Interesting thing is this: if you have got a coil, if you pass a current through this coil, I, a magnetic field will be established around in here. Now, interesting thing is that if you do not have any current source, if you do not have any battery or something, if you have got the coil like this, and you have got just a magnet, you just push this magnet inside the coil, and it just move it around to the left, to the right, to the left, to the right. What happens is that you would be able to read a current and a voltage across the two ends of the coil. Again, this is what Mr. Faraday said. So it means that a changing magnetic field can create an electric current and an electric current can create a magnetic field. That's all about it. So that's what we call the electromagnetism. That is what we call the induction. This induction could be either self-induction or mutual induction. When you say self-induction, is that you've got a coil, you just pass a current, and it will induce an electromagnetic force, or EMF, as you can see in here. Sometimes, no, it is mutual inductance. And this is exactly what is happening in a transformer. Now you have got a primary winding, you have got a secondary winding, and you have got a core in between. As you can see in here, there is no direct touch between primary and secondary windings, right? And these conductors are not, for example, touching directly in there, but you apply something to the primary and you can read something in the secondary, and that's because by means and by help of that core, there will be an induction between primary and secondary that can create things, and that is the base and the concept of the transformer. So a very basic transformer is consisted of a primary winding and a secondary winding and a core. And for your information, that core again is the highway. That core is more like what we had in electricity. Now this is magnetism. This is not electricity. So for your information, when someone says this is a good transformer, they are mainly referring to the core of the transformer. This core of the transformer, if it is good quality, in that case that's a good highway. In that case it is passing the induced charges from the primary to the secondary with no such heavy traffic. And the cars are not going to be strangled in a traffic jam. There is no such traffic jam in here. So that's a good transformer. If the manufacturer, they would like to save some money, they would say, okay, so this is the transformer. Yes, you go to the market, you go to shop number 1. Hey, okay, sir, I would like to have a transformer. What is the voltage ratio? The voltage ratio is, for example, I would like to have an adapter. I would like to connect it to my radio or something. Okay, so what is the ratio? Well, I would like it to be 220 to 6. So that I just connect it to the mains, it's 220. And the result is 6 volts. And I just connect it to my radio. So the first one says, how much? Well, $10, $10. Really? Okay. So the second one says 5. Oh, mate. Okay, just go get the one. So why should I pay $10 for that? I will pay just $5. Okay, so you just get it home. You just connect it to the mains, connect it to your radio, and you have got something like, oh, what's that noise? Why do you have noise? Well, because of that transformer, because of the core. Because of the quality of the core, because of how it's been manufactured, because they were actually trying to save a lot of money. I'm not saying that whatever is cheap is bad, and I'm not saying whatever is expensive is good. No, I'm not saying that. I would say just be careful when you buy something. Not everything cheap is good, okay? There are some reasons behind that, okay? So the thing you need to know about the transformers is just this relation. So when you say the transformer has got a HV side and LV side, it's got a primary side and secondary side, it has got a 220 volt side and a 6 volt side. The way one side of it is 220 and the way another side of it is 6 volts, it has to do with the number of turns of the coil on the primary side and on the secondary side. That N primary and N secondary is like that. So remember that for yourself. Whenever at the side where you have got the higher voltage, it means that you have got more number of turns. At the side we have got the lower voltage, it means that you have got less number of turns. This is how it works. So therefore, at the primary side, secondary side, so the primary side is the HV side, and the secondary side is the LV side. Okay, so the primary side, you have got more number of turns, thick copper wires and less insulation, and on the secondary side, secondary coil, you have got less number of turns, thin copper wires and more insulation. So that is what we call the step-down transformer. So it is changing a high voltage to lower voltage, 220 volts to 6 volts. It can be a step up. So sometimes you've got a low voltage and you would like to transform it into higher voltage. So this is how it works. So therefore, this is the construction of the transformer. We have got different types of cores. It can be steel cores, it could be laminated steel cores, solid cores, air cores, toroidal cores. It has got windings, insulation, shielding, and of course, not for that adapter thing that I said, for big transformers, you need to have coolants. Other than that, there will be a lot of heat, as you can see in here. So you have seen on the big transformers, they have got radiators. They have got oil pumps. They have got fans or something on the transformer just to make it cool, cooling down. Other than that, the transformer will be damaged. Again, I said the differences between three-phase and single-phase. Just for your information, when you talk about three-phase, these three-phase windings of the transformer can be connected in two forms. One of them is delta, which is on the right hand side. Another one is the star, which is the left hand side. And you need to understand that these three windings of phase A and phase B and phase C, like for example, this is phase A and this is phase B and this is phase C, okay, they have got 120 degrees electric degree apart. And then again, this is not the subject of here, but just bear in mind that these generators, when they just create these voltages and currents, they just have to rotate. They have got a stator and they have got a rotor, okay? So it just rotates and rotates and rotates, all right? So as a result of that rotation, the electromagnetic field will rotate with the windings, all right? When the electromagnetic field rotates, it means that these windings are intersecting with those fields, and according to Faraday's law, that induction will happen. I've got a suggestion for the class. For your information, that session 4, okay, takes me less time. But this one and number 3, which is protection, takes me more time. I'll just have a suggestion for you. Let me continue for another 5 minutes so that I can finish this, and then after this I will give you 5 minutes break. Rather than starting with number 3, which is protection, I will start with number 4, which takes me less time, and then I will do session 3 for the last presentation. Are you happy with that? So that we have got better time control. Everyone happy with my suggestion? So please bear with me for another 5 minutes. I will finish this. I will give you 5 minutes break. I will start with harmonics or something, and after that, because protection is important, I just don't want to skip something with that. Okay, excellent. Thanks for your support. Okay, so we have got these things in here, and another thing is the vector group. So if someone asks you about the vector group of the transformer, you would say that depending on what kind of connections you have got, we have got difference in phase between these windings. So you've got a transformer. Look here carefully. These are the important things, and I just don't want you to miss it. So please listen carefully. This transformer, look, it can be delta star or delta Y. It can be delta, delta. It can be star, star, or Y, Y. Okay? So there is no difference between delta, star, or star, delta, or something. Okay? So all in all, when you are thinking of that rotor of the generator to rotate and the electromagnetic fields to rotate, it all depends on how you have connected these windings. Again, the purpose of this course is not for me to get into the very details of that, but all I'm saying is that just focus on these degrees in here. And as a result of these, you will have some what we call phase shift between the two windings of the transformer. And that phase shift is given to you on the nameplate of the transformer as the vector group. And that has to do with the design of the transformer. So if someone asks you, just for you, it's just understanding. If someone asks you what is the meaning of power factor, what is the meaning of power factor compensation, what is the meaning of vector group, you should be able to do that, okay, to respond back, even if you are not an electrical engineer. If someone asks you about the cooling system, you should be able to understand and saying that, especially when you are talking about a big transformer, okay, you are talking about big power, you're talking about big currents. I understand that the consequence of pushing big currents into a copper conductor, for example, could be a lot of thermal energy, a lot of heat. And if you do not find a way to prevent that heat, in that case the transformer would be damaged, the motor would be damaged, the conductor, the cable, the wire would be damaged, the generator would be damaged. So this over temperature at all the time is a big problem. All right, so you need to have coolants in there. It can be water, it can be air circulation, it can be oil or something. Okay, so a transformer must have a cooling system, like what you've got in your car, isn't it, right? You have got radiator, you have got the circulation of water or something in your car. Other than that, the engine is burnt. Same thing applies to transformer. If someone asks you about the transformer efficiency, you would say efficiency by definition means output divided by input. So when I say efficiency is 100%, it means that whatever I have given to the primary side of the transformer, I have received at the secondary side. It means that full efficiency has been covered. I have got a very quick question for the class. In your opinion, what are the things that can be problems in here? Why is that the efficiency of the transformer is not 100%? It is 80%, 90%, 75%. So what are the problems? What are the things that can destroy this efficiency? What are the things that are problematic in here? We are talking about the transformer efficiency. So what is the thing that makes excellent, Hector? So we have got losses in here, right? So the enemy to this efficiency is loss. Now, Jeremy, before I ask the question, you just started that. Excellent. So I'm asking, how many types of losses we have got in a transformer? Jeremy has said the first one, core losses. Perfect. Can you think of any other losses in the construction of the transformer according to what I showed you? Can you find any sort of other losses in the transformer? Core losses is correct, and because that core, I said, if it is very, very, very high quality, in that case the loss of the core is very low. If it is low quality, of course the loss is that is very high. That's perfect. And unwanted resistance pole means what? Okay, so again, Jeremy, you have added another thing which is correct. So winding loss, okay, this is what we call, again, Alec, correct, that conductor loss or winding loss is what we call the ohmic loss. Okay, so ohmic loss, which is the same as conductor loss, which is the same as winding loss, is correct. Core loss is correct. Can you think of anything else? In your opinion, are there any other sort of loss that you may think that may exist in a transformer, and as a result of that you do not get 100% efficiency? Let's have a look. So this is it. Have you ever heard of eddy current losses? Have you ever heard of hysteresis losses? So this hysteresis loss, for your information, that is the core loss, okay? Hysteresis has to do with the saturation of the core. This hysteresis loss is a characteristic curve that has to do with the magnetization and energization of the core. These eddy current losses are some kind of unwanted currents that can show themselves as a result of how you have manufactured this transformer. Like, for example, the let's say the sheets of the transformer core that you put on each other. It is not, you are not going to have a solid object as the current. You have got laminated sheets of iron, for example, or steel, put together, compress them together to get the core of the transformer. Okay, at the end of the day, you are not going to get 100% perfect job. Okay, at the end of the day, you will have some kind of loss. Whatever is your manufacturing company, the best of the best in London or Germany or Holland or whatever, the best of the best, even the best of the best, you are not going to get 100% efficiency in terms of eddy current losses. Well, again, there will be some leakage or something, okay? So we have got eddy current losses, we have got the hysteresis losses, we have got the copper losses or I²R losses, which have to do with the conductor and the windings. And companions and friends, this is the end of this presentation. Now I'm just going to give you 5 minutes break, and I will start with the presentation which was intended for session 4. See you in 5, okay? Be back in 5 minutes. Hello again, I'm back with presentation number 4, which is power quality and electrical safety. I believe you can hear me okay, and you have no problem in seeing the slide. Is that right? All okay? Excellent. So far we have talked about a lot of parameters in a power circuit. I've got a quick question for the class. In your opinion, when we say a disturbance, something abnormal situation, okay, could you give me some examples of abnormal situation in a power system? Like what? I give you the first one. I talked about harmonics, for example. One of them was harmonics. Can you give me some other examples of abnormal situation or case or whatever in a power system? What is the thing that may go wrong? What kind of reading you may have which in your opinion is problem? That pole, that short circuit, you have to think about the result of that short circuit. What is the result of that short circuit? Power surge is correct, line noise is correct. After this kind of things, okay? Abnormal, yes. Interference is correct, and you are not referring to the very, very important things. Sometimes we see the very small thing, but we don't see the elephant. You are not talking about the elephant. You are not talking about the big, big ones. What is the everyday problem? Everyday problem. What is the result of that short circuit or fault? That is the subject of session 3. When you have got a short circuit, when you have got an open circuit, when you have got interference, what is the result of that? Again, the parameters of the power system are current and voltage and power and frequency and things like this. When you have got an abnormal situation like this, what is the result of that? Well, all these things start with either letter O or letter U. That was the key word. So either you will have over current over voltage, over frequency, or under voltage, under frequency, something, overload. Okay? So these are the problems. These are the things that will happen, and you have to think about it. So are they going to damage the system? Of course. If your system is 220 volts, your fridge is 220, your TV is 220, your computer is 220, everything in your house is 220. If all of a sudden, as a result of lightning, as a result of switching impulse, as a result of anything, all of a sudden the voltage in the receptacle and the power point in your home changes from 220 to 400 volts, and no protection, no nothing operates, finish. A lot of things in your house will be burnt. Same thing applies to all the current. Same thing applies to the changes of the frequency. Everything in your home, AC ones, work with 50 hertz. In your office, everything is 50 hertz. If it changes to 55, if it changes to 45, you are going to have big problem. So the subject of my next presentation, which is protection, will show you the importance of power system protection. If you do not have power system protection, if you do not have the fuses, if you do not have the relays, if you do not have the circuit breakers, if you do not have the MCBs and MCCBs, which are the miniature circuit breakers, you are going to get into real trouble. You will lose a large area of your network, and you will have all the household appliances, electrical ones, the kitchen appliances, the shop or office or factory or a lot of loads burnt down. So this is what we call the importance and the role of power quality. So, my dear friends, if someone asks you, are you an electrical engineer? Nope, I'm not. What do you understand from power quality? What do I understand from power quality? What I understand is that this power system that has been given to me by a utility somewhere in Scotland or Ireland or I don't know, Wales or England or whatever, they have guaranteed that this is a reliable source. Reliable? What do you mean by reliable? Reliable means reliable voltage. Oh, okay. Reliable current. Reliable frequency. Reliable phase. That is the quality of the system. This is the power quality. This power company is telling me, I'm just going to give you a single phase source which goes into the receptacles and sockets and power points, and that's going to be 220 volts. I'm trusting this power company. I'm connecting my fridge and washing machine and dishwasher and TV or whatever just because I am trusting in you. Well, if it is not 220, this is what we call the voltage disturbance. You are telling me that the frequency is going to be 50 hertz, and I'm just going to rely on you. If it is not 50 hertz, this is not honesty. You have destroyed my equipment, and I just trusted you. This is the meaning of power quality. If the power quality is not achieved, the power company will lose its reputation and value among the customers. So they will lose, simply, they will lose their customers. So power quality is the first thing that comes in. Apart from safety, of course, it has to do with safety. It can cause fire, it can kill people. It can electrocute people. Well, of course, electric safety, it has to do with electric safety. But we are trusting the power company. Either you're talking about the generation side, transmission side, distribution side. Power quality has to do with all these things. So 3 criteria we have got for a power network to work okay. Other than that, it will not be okay. So we have got the issue of continuity and quality and efficiency. You already know the efficiency. I told you the meaning of quality. And another thing is the continuity of supply. Well, you would like to have the power at all the time. Would you be happy if you have got just outage, an outage, an outage? Uh-oh. That's going to be bad. Either you're talking about a hospital or a school or church or office or home or whatever. Discontinuity or outage or blackout, this is absolutely something that will ruin the credibility and the valor and the reputation of the power company against their customers. This is bad. Discontinuity has to do with power system protection, part of it, which is the subject of my next presentation. Quality has to do with the quality of your system. Good conductors, good transformers, good generators, good connections, good fuses, good terminals, good wires. And it is not just the quality of those, good design, good planning, good management. So all I'm saying is that this continuity and quality and efficiency have to do with each other. They are interconnected. If you lose quality, you will lose efficiency. If you lose efficiency, you will lose continuity of supply, and so on and so forth. They are somehow depending on each other. So as I said, when you say power quality problems, it could be voltage problems, it could be frequency problems, it could be harmonic problems, or whatever, something. So if you have got fluctuations in voltage, you are sitting in your home, fluctuations in your voltage. The TV just gets on and off, on and off, on and off. That's very bad, isn't it? That's disturbing. The lights in your home just become less light, more light, less light, more light. That will disturb your eyes. Not saying about the damage to your lights or something, just burn them out, just to your eyes. You're just going to read something, just going to study something, you are sitting, you just want to be comfortable, you cannot, right? Frequency, a lot of noise, parasite or something, apart from the damage to the equipment. So these are what we call the disturbance. So first of all, voltage variations is not good. If it goes above, it is what we call the over voltage. If it goes below, it is what we call the under voltage. Again, we have got some classifications in here. Now, you're talking about under voltage, over voltage, under frequency, over frequency. So I would say for how long? Is that for long duration, or is that for very, very short and temporary duration? If it is for very, very short duration, I would prefer to call that voltage variation as sag if it is under voltage, or swell if it is over voltage. If it is long duration, no. So when I say dip, voltage dip, it's not going to be long duration. If I say sag or swell, it's not going to be long duration. So there is a difference between the definitions, because the reason we are just separating these items, these definitions from each other, that's because of their consequence. Because the consequence of a sag or swell is much different from a long under voltage or over voltage. That's why. Let's just have a look at this and remember this. When we say voltage sag or dip, it means that if you have got, you remember that maximum, I max, V max, and RMS or something? I'm just talking about that max, okay? So forget about that RMS. I'm just talking about max. It says, first of all, it's a decrease between 0.1 and 0.9 per unit. Just memorize for yourself. This 0.1 per unit means 10%. 0.9 per unit means 90%. So if temporarily, very, very quickly, what do you mean by very, very quickly? This is it. Between 0.5 cycle to 1 minute, you understand the meaning of 0.5 cycle. In the UK, frequency is 50 Hertz. 1 divided by 50 makes 20 milliseconds. That's 1 cycle. Half the cycle means half the 20 millisecond in the UK, which is 10 millisecond. This is what we understand. 10 millisecond, 20, 30, 40, something, okay? If it is a very, very short period of time, where you have got that voltage drop. So a voltage drop for a very, very short period of time is what we call the voltage sag or dip. That drop could be 10% drop, could be 20% drop, could be 80% drop, could be 90% drop, and that is the meaning of the voltage sag. So causes what? Local and remote faults. Very, very bad faults. Even if it is 10 milliseconds, 20 milliseconds, oh, it was nothing, mate. It was just half a millisecond. Well, whatever. Yes, you think it was very short, but it damaged a lot of things. So that's the meaning of voltage sag or dip. You would not believe, but it can impact a lot of things like computer crashes, bulbs glow dim, fan speed reduces, effect on motor speed, poor TV video quality. Well, we can tolerate poor TV video quality. We can tolerate bulbs glow dim. But when it goes to industry, the effect on motor speed could be absolutely catastrophe. Okay, that's bad. Fan speed reduces in industry. In that case, you will have overheat. All of a sudden, a $10 million asset is burned in front of your eyes in less than a minute. $10 million asset right in front of your eyes because of the fan speed reduction. Oh, just because of that 30 millisecond. Oh, yes. This is it. This is what you've done to me. Just as a result of that short time voltage variation, this is exactly what you've done to me. Same thing applies to voltage swell. Well, you told me 100% means 220 volts, yes. So you just had an increase of 10%. Now this is increase 1.1, or even between 10% to 80%. You know what you have done to me? Oh, mate, it was nothing. Just look, it was just for half a cycle to 1 minute, whatever. Whatever. You just damaged a lot of things. The protection system didn't work. And that's it, just because that was a very short period of time. Even you caused a single line to ground fault. You just damaged the insulation material. Remember, write down for yourself or remember, the effect of over voltage at all the time is damage to the insulation material. When the insulation material is damaged, fault will come. That's how it works. So there again, especially electronic devices, very, very sensitive they are. TV, smart TV, digital TV, computers, wow, right in front of your eyes, they will damage everything. Thousands of dollars or pounds you have already paid for that. The small fuses in electronic equipment will blow off. Bulbs of low power rating will blow off. Even the surge arresters or MOVs will operate. So that's the effect of that. You cannot simply ignore. It can be even an overvoltage, which means longer than 1 minute. Okay, the worse. The worse. Wow, mate, it was just 10%. Just 10%? Yes, but it was more than 1 minute. 10% more for more than 1 minute. You know what you have done to the system? So like what? Like load switching off. Load switching off, yes. So what's the problem with that? What's the problem with that? You know what site is this? No. That's a mine site. Okay, mining. Yes. What kind of mine is that? Gold mine. Oh, okay, gold mine. Yes. As a result of that over voltage for more than a minute, even for 10%. You know what you have done to us? No, what's done? Okay, so you caused an outage to this production line. Yes. You know what is our loss per minute? No. Well, I would say $10,000. Really? Yes. And guess what? Guess what? Tomorrow, I'm just going to sue you for this because you have caused an outage of 2 hours to my system. And each minute, I'm just going to sue $10,000. Wow. Oh, yes, you have done that to us. As a result of that, I asked you, I've already paid you a lot of money. What I asked you was power system reliability. I told you I'm going to have zero tolerance over any problem in here. I'm not going to tolerate 10% over voltage for longer than 1 minute. You destroyed my motor. As a result of that, this conveyor belt is stopped. As a result of that, this ore, this rock that contained gold stopped in here. As a result of that, the leaching unit and the smelter unit did not have any infeed. As a result of that, there was no gold metal extracted from the rock. As a result of that, you see those lorries, you see those ships? Well, that's the end user. They are waiting for that. You know how much I have to pay them per hour of failure? That sorry, mate, you have to wait in here because I don't have any load for you. They are paying a lot to the port or something like that. See, this is going to be very, very complicated. This is very, very complicated. So therefore, in my next presentation, I'm just going to prepare your minds for my next presentation that when I say power system protection, protection is absolutely important. That can save you millions of dollars when you think about that. Don't ignore anything. Just mate, this is just a fuse. No. Even that fuse can save hundreds of thousands of pounds of dollar for your industry. Don't underestimate these things. So look, the impact could be electronic devices will burn, refrigerator will blow off, winding of motors of fan mixers and grinders will burn, overheating of equipment, bulbs will blow off, fuses will blow off. Well, that's very bad. Absolutely, this is massive. Same thing applies to under voltage. Oh, okay, so rather than 220 volts, I gave you 200 volts for more than 1 minute. Really? You know what you have done to us? No. Okay, so even for that under voltage, video on the TV will not appear. Mixers and grinders may not start at all. Computer crashes. When you say computer, I'm talking about the server computers. The whole network, all of you every day just log on. The whole office, 5,000 people are sitting in your office, say. All of a sudden, everything down. Everything is just going to the kitchen. You're just having your cup of coffee. Ha, 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 he, he. You know how much loss is to your company per minute? Per minute, how much pounds of loss as a result of computer crashes so that the IT people can restore everything as a result of that. That's massive, massive. So we cannot underestimate things like that. Maloperation of refrigerators, it may be for home, not for industry. It may be tolerated even if the food stuff will go off, I understand. But when it goes into the industry, refrigerators can cost hundreds of thousands of pounds or dollars actually to the industry. So we cannot ignore all these things. So what are the things that may go wrong? Do you remember that three-phase system I told you? You remember that you need to have a balance between the loads if you decide to make it a three-phase as opposed to single-phase. You need to have a balance. You need to have a harmony between the phases A and B and C. Therefore, when you invite a technician to come to your home, to your office, you would say, at the moment, we do not have any power in here, mate. We want you to put a switch box in here and allocate one switch, for example, to room number 1 and 2, one switch to room number 3 and 4, and so on and so forth. So the technician would think, okay, so this is an office, right? So to me, the importance of room numbers 1, 2, 3, 4, 5, 6, 7, they are not the same. How come? Well, this room number 5 is a conference room. Oh, okay. Room number 2 is just the room for your manager. Okay. Room number 3 is where you have got your kitchen appliances or something like that. So it's more like a kitchenette or something. Okay, all right. So the kind of loads that you are connecting in here are much different between your conference room and the kitchenette and the manager's room or something. So I have to think for myself, how can I distribute the loads between the three phases so that I have got almost the same thing? Look in your house. You have got bedroom number 1, 2, 3. You have got lounge. You have got kitchen. You have got living area. You have got study area. You have got the theater room. Well, whoever has designed the electrical system in your home, when you look into your switch box, you have got laundry. They understand what you are going to put in the laundry. And they understand what room or area in your room can share with laundry, because they fully understand you're going to put your washing machine in there. So there is already a big load in there. So the one that is going to share that load with laundry should be a low consumption load. See, this is how it works. If you care about these things, you are going to have a fantastic load contribution. So that is at the load side. Same thing applies at the generation side. Now, I'm talking about the power company. Zoom out. You are sitting in your home. You are seeing your own loads. You are seeing your washing machine, dishwasher, TV, whatever. Now, let's sit in the power company. You are seeing the whole lot. You are saying this is east of London, this is west of London, this is north of London. That's a big, big load, London, for example. And now zoom in. Now, if you're talking about North London, I am just going to divide it into a matrix. Cell number 1, cell number 2, cell number 3. And again, within cell number 1, you have got Smith Street, you have got Baker Street, you have got so on and so forth. So you need to have a very, very good understanding about how much load, how much current is per street. And then you would be able to put the cables in. Oh, okay, so that is how the system works. If you make a mistake, in that case you will have load unbalance. When you have got load unbalance, you have got voltage unbalance. When you have got voltage unbalance, you have got trip, you have got outage, and you have lost the power quality. Easy. That's why as soon as you guys as loader are going to do anything, any changes in the system, the power company must be aware of that. If not, they will lose the balance on the system, and that will be a tragedy. Again, you can see the causes and you can see the consequences, the effects Absolutely bad, from increased vibrations and mechanical stresses to increased losses to, I don't know, a lot of phase current unbalances, why the insulation material being degraded, a lot of things like that. Again, worse than that is periodic voltage fluctuations. If that happens, your system is absolutely unreliable. So causes arc furnaces, intermittent loads, reciprocating pumps, and the impacts: lightning flicker, maloperation of electronic equipment, maloperation of sensitive loads. These days, your life, my life, everyday's life, fortunately or unfortunately, in the 21st century, is based on electronics and digital technology and computers, server computers and LAN and WAN and communications and router or something. When we say sensitive loads, they are sensitive loads. If this kind of thing, just put these things down, in that case you will lose your access to your internet banking, you will lose your access to your shopping online, you will lose your account, you will lose access to email. That's a tragedy. These days, even one day, we cannot live with all these things. With your smart mobile phone, with computer, with email, with online banking, with online shopping, with eBay or whatever. Even one day you cannot live like that. The whole life is based on computer and digital technology and communication. So when we say sensitive loads and electronic loads, it means the whole life will be affected tremendously. Even you think about frequency, yes, frequency, deviations from 50 hertz to 60 hertz, that's absolutely bad. Poor speed regulations of local generation, well, that can cause faults on the bulk power system, large block of load being disconnected. When we say bulk power system, if you have got, I'm not talking about the far off region in the UK or something, I'm just focusing on London, say. That's a bulk power system. Even a small part of that, if you have got a frequency variation, that is more like a domino. That's what we call the cascaded faults. If you don't stop it exactly like domino, you would not believe that in less than a minute, you are going to lose a huge part of your network. In less than a minute, even for this frequency variation. This is what we call the frequency drift. Like what? Blackout. Really? Yes. Blackout in a very large area. Transformers will blow off. Just think about that. Equipment failure, motor windings will burn. Due to what? Due to overheating. Motors in mixers, grinders, fan will burn. Oh, that's absolutely massive. That's absolutely bad. Surge. Surge comes from where? Over voltage, yes. One of the sources is lightning. Lightning, yes. If you don't have lightning arresters, if you don't have surge arresters, you are going to have like a bomb. Believe me, the transformer will explode like a bomb. Okay? The generator, the transmission line. You need to have good protection like this. It starts from your home. For very, very simple loads, you need to have such a thing. Surge protector, you need to have such a thing. You pay a lot these days for this kind of protection, but it's worth it. You have got a TV. That TV, I'm not sure about pounds or something, but I can tell you it's at least something like $2,000 Aussie dollar, $3,000, $4,000. That's too much. You have already paid a lot of money for that. So it's worth if you just put something like a protector, something like that. Just for your information, that surge is not necessarily coming from lightning. It can be from switching operation. When they operate the circuit breakers, the big ones, it's going to make an impulse in your system. This is what we call the switching surge, which can be load switching, oscillatory switching, capacitor switching. It's going to happen all in their substation. You are innocent. You have done nothing. But the power company is doing that. Power system recovery, fault clearing, arcing faults or something. The result is that your system is down. Or it can be the act of the nature, lightning. Okay, in that case you need to make sure that you have already applied adequate and appropriate protection against that lightning. For example, by means of those lightning arresters that you can see adjacent and next to your transformer, adjacent and next to your transmission line, and other valuable and important and strategic assets. As I said, it can be a lightning surge, which we cannot stop, but at least we can protect ourselves against it, or a switching impulse or surge. Therefore, these surges, wherever they are come from or originated from, the effects are, again, get back to electronics. Electronic devices may operate erratically. Equipment could lock up or produce garbled results. Electronic devices may operate at decreased efficiencies. That's absolutely bad. Integrated circuits, that is electronic integrated circuits, may fail immediately or fail prematurely. Most of the time the failure is attributed to the age of the equipment. See? That's it. Again, if you lose electronics, if you lose power electronics, if you lose the computer service and internet or whatever, LAN, WAN, Ethernet, router or something, that's going to have a widespread effect all across the country. It's not going to be limited to an area. So we have to start protection against this kind of system disturbances and abnormalities from our home. Something like that. You can have a very, very simple receptacle, or you can have an anti-surge power point, at least in your home for critical devices. Especially if you are working or living in a skyscrapers or multi-story buildings or something, you may have noticed that on the roof we have got a big metal bar rod. That is the lightning rod. So it will attract the lightning, and as you can see in here, it's been connected to a wire, a conductor. And what it does is that as soon as you have got a lightning in here, it will be attracted by this rod, and the massive current will be conducted down to the surface of the earth. So it's more like a sacrifice, self-sacrifice. This rod is doing a suicide just to protect the building. So it will conduct hundreds of thousands of amps, which is as a result of the lightning to the pavement. But that pavement is not going to kill someone, because underneath the pavement you have got a very, very complicated and comprehensive earthing system. So that massive short circuit current under good design should be dissipated away into the matrix and earthing network that you have previously established underneath the ground at an appropriate depth. This is how it works. Again, the purpose of this course is not going to get into the very details of that, but for your information, we have got other courses for the earthing design, for the protection design or something. So if you are interested, you would be able to continue like that. But the aim for this course is just to give you a preliminary understanding about how it works and what's the purpose of that, without getting into the very detail of the design or the parameters. I talked to you about the harmonics. You told me that it means the multiples of frequency. That is exactly right. But for you guys actually to understand from these courses, that if someone asks you, okay, you're talking about harmonics, yes, so you're talking that harmonics is just having multiple frequencies in addition to the base frequency. Yes, that's right. And you are saying that, okay, so the effect of that is that will do it to our motors and generators and transformers and, I don't know, the panels and bus bars or whatever. So I understand all that. I've got a simple question. Yeah. So my question is, where comes this harmonics from? Why should we have this kind of harmonics? In other words, I'm asking, what are the causes? What can cause harmonic in a system? That's the question from your cousin. That's the question from your brother and sister. Easy. If I'm a teenager to you, I understand the meaning of harmonics. Okay, I'm just going to avoid that harmonic. What are the sources of harmonics? What's the answer? Non-linear loads. In very general terms. Non-linear loads? Yes, like what? You see these fluorescent lamps? Yes. Well, in your home, how many of them you have got? Well, maybe one, two, not a problem. Look in your office. Oh, look at each hole. Oh, my dear, there are all fluorescent lamps. I've never noticed that. Why you have got so many fluorescent lamps in your office? Well, when you energy saving. Oh, energy saving, yeah. Because when you compare them with incandescent lights, 100 watts, 200 watts, 50 watts, well, when you compare the usage, consumption of that fluorescent bulb, it's more like nothing. So you are paying a lot less to the power company, a lot less, yes. But you have got a compiled, accumulated of that non-linear load in there. Okay, so just for your information, these heaps of non-linear loads that you have got, that they can create a lot of harmonics. Okay, so the effect of that could be frequency drift. Wow. Okay, yes. The effect of that could be unbalance of load. The effect of that could be overheating. And the impact of that could be damage to your cabling system, could be damage to your internet and computer server system. And for your information, that damage could be in the order of $50 million. Are you ready for that? Wow, okay, yes. So you are saving energy by doing that, but at the same time, you are exacerbating the situation for harmonics. Uh-oh, no. Okay, so what am I going to do? Put harmonic filters. Oh, okay. So, but the cost, we have already made a quote. It's going to cost us $150,000, whatever. I'm telling you, they can damage $50 million in here. That's your decision. That's it. You are the manager here. Make a decision right now. That's a hotel. Lots of fluorescent lamps in here. So is that the only non-linear loads? No. We have got variable speed drives in industry. What is variable speed drive? Well, variable speed drive is that kind of machine that is whose speed is a parameter of frequency. Oh, okay. So you are going to get some kind of different torques out of that machine. Yes. So rather than changing the voltage, rather than changing the load, you just change the frequency intentionally so that you can have a control over the speed of the machine. Wow. Okay, yes, it is a real wow in terms of the NEAL technology, but at the same time, it is causing a lot of harmonics in the system. So you have to be prepared for that, and you have to provide enough harmonic filters. Other than that, you have got fuse and breaker maloperation, communications interference, equipment malfunction, voltage harmonics, process problems, a lot of things, conductor overheating. So you have to compensate. You have to eliminate this kind of harmonics from your system. Other than that, you are going to be on the real problem. So how do I know about the minimum requirements so that I make sure that I have provided reliable power for my customer all across the UK, say? Well, we have got codes. We have got British standards, BS. We have got Aussie standards, AS. We have got American standards, IEEE. We have got European standards, IEC. We have got codes of engineering practices. We have got electrical safety standards and practices. So from this page on, this presentation will tell you some dangers that you may have if the design is bad. The problem of electrocution, it can be arm to arm or arm to leg. Again, for the purpose of this class, you should be aware that a short circuit that goes through your body, we are considering a person, a male, with an average weight of 70 kilograms and the height of 170 centimeters. These figures are valid for that person. If you're a female, if you are shorter, if you are weaker, in that case, you have to be more careful about this figure. So for that particular male, a 1 milliamp is the margin of perception. It will just give you a tingle. 1 milliamp. You just feel it. If it's in the order of 9, 8, 10, you just let go. It means that, oh, I cannot continue like that. It's a shock. But it's still not a big shock. If it's in the order of 16 milliamp, is the spasm. And that thing is that you cannot let go. And that's how it is. Between 70 to 100 milliamp, constriction, muscles, heart muscles or something, and death. So this is the dangerous current flows. So all in all, we have to be very, very careful about the either direct or indirect touch to the live compartments. If it is direct, that's the worst case scenario. You're just directly touching the bare conductors. Sometimes it is not direct, it is indirect. What? How? Well, you've got a piping system. Yes, you go to the laundry. Yes, you are innocently going to turn on your washing machine. Yes, so you are touching the valve. Yes, that's a water pipe. Yes, and poof, you are electrocuted. Why? Well, because somewhere else a live conductor has been connected to your piping system, not necessarily in your lounge, but the effect of that will be felt in your area. So, I'm in the industry. How am I going to protect myself? You have to have the PPE, personal protection equipment. Like what? Like gloves, the safety boots, helmet, or hard hat, goggles, overall, things like this. So you have to safeguard your arms and legs, your foot, your head, your eyes, your ears at times, your body, things like this. Even if that place is producing a lot of noise, you need to have earmuff, safety helmet, safety goggles, safety shoes, boots, safety gloves. So this is what we call the PPE. Again, if you are in a dangerous area, you should use tags, danger tags, notices, caution tags, notices. I'm pretty sure in your office you have got first aiders, for example. There are people who are voluntarily doing this and they have already been trained for first aid. So first aid is very important. You're going to preserve lives. You are going to prevent people being damaged or something. You have got some responsibilities. You should have received enough training. You should be prepared for the emergency situations, especially breathing problems, heartbeat failure, severe bleeding, unconsciousness. So these are the important things. Especially if someone is electrocuted, you must try not to touch them, unplug the appliance or turn it off, and do not try to move the victim and keep the victim lying down. The rest of this presentation is just for another few pages, and I'm pretty sure you understand the whole lot. It's not very difficult. So the code of practice, and just give you some, I don't know, the examples of some standards like BS415 and 4743 and some other things that I'm pretty sure you understand, and your knowledge is a lot higher than that. And then again goes into the Australian standard AS3000, which is about the wiring and the applications and where you have used that. Okay, so that's the end of this presentation. I'm just going to give you another 5 minutes break, and I'll see you in 5 minutes. Happy guys? So far so good. So if you've got any question right now, please ask. And other than that, I'm just going to move on to the next presentation, right? Happy so far? No questions? Nothing for me? All okay? Excellent. So I'll see you in 5 minutes. Thank you. Okay, everybody, I'm back, and this is Power System Protection session for the EN workshop. Could you confirm you can hear me okay? And you can see the slides. Ready? Okay, roger that. Excellent. So far, I have already prepared you to understand the importance of power system protection. Either it's going to be fuse protection or relay protection. Okay, before I continue, if I ask you a simple question, if I ask, okay, all of you have seen fuses. You have got a lot of fuses in your home, fuse box. You have seen the fuse box in your office, okay? And also you may have seen protection relays, okay? Can I ask who has ever seen protection relays? Hands up or put a tick mark or say yes, okay? Tick mark for me or hands up if you have ever seen and experienced protection relay. No one? Who has got any experience with protection relays? Okay, right. So I'm asking this question. If someone asks you what is the benefit of fuses, fuse protection, as opposed to relay protection, can you tell me some of the benefits of fuse protection? What are the good things about fuses? What do you understand about fuses? What is the good thing about fuse protection? We have got thousands of them in our system. Instant blow, I accept. The fuse blows rather than the electric item. No. I understand the, let's say, the function of fuse, Carol. I'm asking between relay and fuse. What is the advantage of fuse to relay protection? So instant blow is good. Cheap is the answer, okay? Very good. So they are cheaper. You can reuse it, okay? What else? That thing, Hector, you said can be a disadvantage as well. I'll let you know in a minute. So that can be a disadvantage as well. Okay, so fuses are, you have not referred to something, are simple. They are simple to understand. They are not very complicated. They have got only one curve. They have got only one operating time. Okay, that's it. So very simple to understand. Cheap. You can have thousands of them, especially in the distribution system. But I can find a lot of problems with fuses. So again, who can tell me problems with fuses, the disadvantages of fuses? Who can say that? I'm intentionally not turning over the slide pages. I'm just trying to negotiate. So what happens, Alec, is that yes, once it blows, you have to bin it, okay, finish, okay? But for a relay, you can reset the relay. You cannot reset a fuse. Paul, you are saying degrade over time. Excellent. It has got a name, and the name we use in English is aging. So these fuses are exposed to aging, while the relays, well, you are just keeping in the panel. It can work for you years and years and years. It's not exposed to dust and humidity and corrosion or whatever. That's perfectly right. And what about curve? A fuse has got only one curve, but a relay has got a lot of curves. As a result of that, you have got relay settings. You have got time settings, you have got current settings. The fuse does not have any setting. Fuse is fuse. Yes, it has got a rating. It's a 2 amp fuse, 4 amp fuse, 8 amp fuse, 16 amp fuse, whatever. That's it. There is no setting on a fuse. Relays can be remotely controlled. How? By means of comms, communication, by means of SCADA, PLCs, RTUs. What about fuse? No. No remote control. There is no nothing. Except for some advanced electronic fuses. I'm not referring to them. I'm just referring to conventional fuses. No remote control. Yes. No comms, no SCADA, no nothing. That's fuse is fuse. So what's the problem? The problem is, if you have got a fuse far away from your depot or office or something, if I tell you, hey mate, the fuse is just blown up. It's in a farm very far from the CBD or something. So you have to send a technician with the van, or I don't know, ute or whatever you've got in there, just to go there. First of all, get the appropriate fuse from the stock. Takes time. Go to the site. Gets time. Replace the fuse. Takes time. And the customers have to tolerate the outage. That's the problem. What about relay? No. You can easily restore the energy quickly, even if the relay has been tripped. So if this relay is so good, why do we need fuses? That's because of the price. Because there's huge difference in price. And now, good thing about fuse is that the fuse by itself is a combination of protection and switching. You don't need to connect anything to the fuse. But for a relay is just a protection device. It is not a switching device. Now you tell me, what is the name of the switching device that works with the relay? So the relay sends a trip signal to that equipment, and that equipment switches, not the relay. And what is the name of that? So the relay works hands in hands with another device. We have got another term for that, Jeremy. So contactor is more like what you use in a very, very low voltage. So these contactors, they are inside something. And the name is circuit breaker. Okay? Yes. You need to have a circuit breaker as a switching device. You need to have a relay as a protection device. And for your information, that relay needs to have some inputs. Input of current, input of voltage. Do you know where comes that input from? Where comes the input of current? Where comes the input of voltage? The fuse again doesn't need that. But the relay does need that. Have you ever heard about CT or current transformer? Have you ever heard about VT or voltage transformer? So these things are required for relay protection, but they are not required for fuse protection. Okay? So all I'm saying is that if you have got a feeder, something like this, okay, so this is a bus bar, all right, and that's a feeder. You know the meaning of feeder, right? So it's a transmission line, for example, something, and that goes to an area. This is the circuit breaker at the location of the substation. At the same time, you can have, for example, distribution transformers in here. This transformer can be fuse protected. So this fuse is what we show like this. Okay, so that's it. So just one fuse. What about relay protection? See the circuit breaker on top? I call it CB1, right? This is just a switching device. You need to have a relay. This relay will command this circuit breaker by sending a tripping signal to this circuit breaker. However, you need to have input to this relay, and that input is coming from a CT, which is a current transformer. Also, on many occasions, you need to have a voltage input, and that is what we call the VT, or voltage transformer. Again, connected to this relay. So when you are referring to this relay protection, you have to pay for the relay, you have to pay for the circuit breaker, you have to pay for the CT, and you have to pay for the VT, and you have to pay for the connections or what? To have a complete system. Moreover, you have to pay for comms, you have to pay for SCADA, PLCs, RTUs, and everything. Router, modem, dish, antenna, whatever. See, you're going to have a complete system, isn't it? So you have to pay hundreds of thousands of dollars or pounds to get it established. Well, is it worth it? Well, it depends. Are you talking about the transmission line, or you are talking about the distribution feeder? This distribution feeder, where is that? You see that alley? Yes. Do you see that small street? Yes. Well, we have got 10 houses there. Well, I would say fuse. It's not worth it. Per house, I'm going to have that relay protection. Yes. In that case, just a very small bit of your network, somewhere, I don't know, around your city, that will cost millions of dollars or pounds. We can't afford such a thing. That's why these days you can find thousands and thousands of these fuses in your system. Yes, everyone knows relay is better. Relay is more accurate. But sometimes I would say, okay, put it this way. What would happen if I lose this feeder? If you lose this feeder, yes. Okay, so see that street? Yes. 20 houses, they will have an outage. Okay, that's one thing. What about if I lose this feeder? Lose this feeder? Yes. Well, I would say Trafalgar Square will have an outage. You tell me which one has got more severe damage in here. I don't know. This is an area, I don't know, in area in the central CBD of London. You're gonna lose power in there. Wow. Even if you say this protection system is going to cost you $5 million, we will have to pay for that, right? That's going to be very bad if you lose that. This is not tolerable. You need to have the best of the best protection in there. It's worth it. It's worth it. This is central London, isn't it, right? CBD. That's it. This same thing applies everywhere. You're talking about Sydney, you're talking about Melbourne, you're talking about Washington, D.C., New York. It's not a joke. Whatever is the cost, you're going to pay for that, because this is absolutely critical. Not in the regional, nope. Not in a far-off area, no. I'm not going to have that kind of complicated protection for every feeder. No. Maybe the top one, yes. The top supply, the main supply, yes, but not for all the spare lines and whatever that you've got. No, I'm not going to have. Other than that, the cost of that I would not be able to afford. So therefore, you need to understand the kind of fault that you have got. If that fault is going to happen somewhere very far from the CBD or something, the amount of current, of that short circuit current, could be very low. So in that case, you would say even a fuse protection would be enough. However, when it goes into the central business or something area, in that case, even a short circuit, three-phase, that's a very, very strong, solid fault. That can endanger the lives of the people. That can endanger the life of all the assets you have got, and in less than a minute, you're going to incur a loss of millions, if not saying billions of pounds. So you need to have a very, very complicated, strong, well-designed, comprehensive protection system against all these faults. So we are referring to electric fault, short circuit, three-phase, face-to-face, single-phase, to each other or to the ground. So these are the things that can kill the power network. These faults can be permanent, can be transient. Like what? It's a windy day in the UK somewhere. Very, very windy day. You have seen those three phases on top of the wood poles or something, okay? As you drive along, getting out of the CBD onto the roads, you can see either towers, wood poles, steel structures, or whatever. Especially for the wood poles. Well, you have seen in your street, in your alley, you have seen these wood poles. Yes? So you can see the three line conductors are pretty much close to each other. Yes, but they are not touching each other. Yes. I'm telling you, it's a windy day. Well, still, they are not. I'm telling you, that's a big storm. Okay. In that case, that's different. First of all, these phases, the three phases, may touch each other first. Second of all, they have got some objects floating in the air. Like what? Like wood, for example. Like tree branches or something. Well, okay, it is quite possible that these floating objects or the wind itself causes at least two phases to touch each other. All right, but is that a permanent fault? No. It will go away in, I don't know, millisecond or something. So that was just a temporary fault. Yes. So if you look at it like a permanent fault, in that case your system will incur an outage for minutes, for more than minutes or something, and in that case that's not good. So who knows the name of the switching device which is responsible for transient faults? It means that unlike a circuit breaker, it's not going to give you a permanent trip, but it can restore the energy if it understands that it's going to be a transient fault, not a permanent fault. Who knows the name of that? The name is in this page. So it's not a circuit breaker. It's pretty much similar to a circuit breaker, but it's a kind of circuit breaker that will again get itself closed after a short period of time, just to make sure that it was a transient fault or not. So the name is the recloser. Okay, yes. So a recloser switch is the kind of circuit breaker, say, that as soon as you've got a fault, it will open, right? But again, it will more like a timer, for example, right? It will wait 1 second, 2 seconds, 3 seconds, something, and then again it will close again. That's why we call it the recloser, just to make sure that the fault's gone. If the fault is still there, then again open, and then count down 1 second, 2 seconds, 3 seconds, and then again open, close. If the fault is there, again open. If it's a 3 shots recloser, again 1 second, 2 seconds, 3 seconds, poop, close, and then if the fault is still there, it's not a transient fault. It's a permanent fault, and it will lock out, and it's a permanently open. So these are the things. So for the protection of our family, for the protection of our staff and personnel, for the protection of the public, we need to have protection system in place for very, very simple things in our home to industrial applications and business applications. So that's the need for protection, to maintain safe and economic operation of the systems so that we do not have outage, we have got continuity of supply, we have got good power quality, we have got system reliability, the customers can trust us, and at the same time, as soon as there's a fault, we just make sure that we just isolate the fault from the rest of the system. This is what we call the minimizing the effects of fault. Just remember that if there is a fault, it all depends on your response. Either you are going to isolate that faulty part in 1 second, or half a second, or 10 milliseconds, or half an hour or something. The quicker the better. It's more like a surgery operation on heart, surgery operation on brain or something. The quicker the better. Other than that, the patient may die. Same thing applies to power network. As I said, it's more like a cascaded phenomenon. It's more like a domino. If you don't stop it, first it starts from one street. Then in a very, very short time, there'll be 10 streets. Then that'll be half the city, and that'll be the whole city, and that'll be the neighboring city, and it goes on and on and on and on, okay? So all of a sudden you have got a huge and widespread blackout in 10 cities. That's how it is. So you have to, it's more like a virus. You have to stop the virus. Other than that, it will spread itself. So this is what we call the isolation of fault. You have to isolate it. You have to minimize the effect of that fault. Other than that, it's exactly like a virus, okay, that can get the whole part of the body. This is exactly what you do when you've got bleeding, for example. You just try to stop it. You just try to not spreading that to other parts. You've got a burn, you've got bleeding or something. Exactly. This is it, what we have got to our bodies. This is what we need to have to our power system. So this is the meaning of power system protection, but you can do it by means of fuse, or you can do it by means of relay protection. So that's to safeguard the entire system, to ensure the continuity of supply, to minimize damage and repair costs, and to ensure the safety of the personnel. So safety comes first, wherever you are, America, UK, Australia, New Zealand, Asia, wherever you are, safety comes first. And then comes the asset. Then comes damage to the equipment or something like that. So first thing is that we have to safeguard the lives of the people, the public, the personnel, our family, ourselves, whatever. And then minimize the effect of the damage to the equipment. So that kind of electric fault could be something like overload. So what's an overload? Okay, what's an overload? Yes. You buy a TV, all right? Yes, it comes with a power cord wire. It's been well designed for that. You can see the thickness of that. Then you buy a washing machine. In your opinion, is it correct to say that the thickness of a wire of a TV is the same as the thickness of a wire for the washing machine? In that, that's not it. Is that right? So the washing machine is a much stronger load than a TV. Therefore, its wire must be a lot stronger, must be able to pass a lot more currents. Yes? So if you have got a piece of equipment, either a wire or a cable, a conductor, a transformer, anything like that, okay? If you pass current more than what was expected, in that case it is overloaded. That expected that I said in electrical engineering, that is what we call as rating. We say this is a 10 amp wire. This is a 20 amp wire. This is a 50 amp wire. This is the rating of that. This is a 10 MVA transformer. This is a 5 MVA transformer. This is a 250 kVA transformer. That's the rating of that. If you put more load on that, in that case, that device is overloaded. Now, someone in this class, please tell me, what is the immediate effect of overload? Anywhere, on a wire, on a cable, on a line conductor, on a transformer, on a generator. You guys are perfect, magnificent, and I love this audience in here. So that's heat. Let us say overheat. Now, let's cover. Let's see how much you have got out of this class. What is the effect of heat? Heat is bad. Okay, tell me. I'm a teenager. I would like to learn from you. So, cable melted. Something in that cable would be damaged, Hector and others. What is the immediate effect of heat on things? Something will be damaged. Excellent, Maria. Insulation. Okay, so the thing that comes out of overload is heat, overheat. Then the effect of overheat is damage to the insulation material, right? Okay, so therefore, yes, Jeremy says conductance, affectance, and machine affected. Perfect. I'm saying that if the insulation material is damaged, then what? What would happen? Let's cover up. I just want to make sure that we are on the same page. So, short circuit, Alec. Wonderful. Excellent. Short circuit. So if that short circuit occurs, what's your expectation from this system? What you would like? Yes, risk of electrocution. So in order to avoid the risk of electrocution or something, there is the need for what? There is a need for, yes, protection, say, okay? So the whole story starts from there. We have already designed a system. Everything works perfectly well until the time that someone carelessly does something. Overload. Overload brings about heat. Heat brings about damage to the insulation material. Damage to the insulation material brings about fault, which could be short circuit, and then comes the arc, the spark, big fire, and so on and so forth. So what is expected from the system is that you would expect this protection system to operate pretty much quickly. Either fuse protection or relay protection. This overload is what we call, let's get back to the beginning, incipient fault. So what's that? A fault that takes a long time to develop into an insulation breakdown, normally caused by partial discharge or long-term overload. What I'm saying? What am I saying is that if you ignore this overload, saying, oh man, this is not a fault, it's not a puncture, for example, to a cable, it's just an overload. So, well, it was just a little bit of overheat. Why are you making a big story something? Well, anything happened? No, I was there 5 minutes, 10 minutes, nothing happened. Yes, you're right. Nothing happened. But all I'm saying is that you were never supposed to operate, to use this transformer like that. That was the rating given to you. You exceeded that, not just one time, 2 times, 10 times, 20 times. Why did you do that? Well, you know, we have got a lot of load these days in the UK. So, well, it takes a lot of money. I don't know. I have to spend a lot of money actually to buy other transformers or something. So, well, I'm trying to much as I can. I would like to make the most of the existing transformers. Oh, really? So did you know that you are overloading them? Well, yeah, I understand there's a bit of overheat or something. And I was there. Nothing happened. Yes, nothing happened immediately. But it's more like something like decay in your tooth. Yes, that decay in your tooth is not happening in one day. It may take 6 months or 4 months or 3 months until the insulation material in your teeth degrades. This is exactly such a thing happening in cables and transformers. Maybe not now, maybe 6 months from now, 3 months from now, you will hear about that. That's the incipient fault. But solid fault, nope. It has got a very immediate result on the system, like a direct short circuit. Okay, that's another thing. So when we think about overloads, it has to do with the type of load that you have got available: TV, fridge, washing machine, whatever. So you start appropriate loading of the system from your home, and then into the shops and the malls and the markets, and then to the offices, and then to the industry, and the story goes on and on. Now let's forget about overload. I'm talking about real faults. We have already covered that. Overcurrent, over voltage, under voltage, over frequency, under frequency. My dear friends, I'm telling you, now that you understand the disturbances to the power system, therefore, you can imagine for yourself, even if you may not have seen them before, you can imagine for yourself that from this discussion, we should have current relays, or better say, over current relays, over voltage relays, under voltage relays, over frequency relays, under frequency relays, so that as soon as the current, the expected current, goes above the rating, the relay will operate and will trip the circuit breaker that is connected to that. If the voltage of the system goes above the rating, the over voltage relay would operate. If it goes below the rating, the under voltage relay will operate. If the frequency goes above the 50 Hertz, the over frequency relay will operate. If it goes below the 50 Hertz, the under frequency relay will operate. Since I've already covered session 4, you already know the effects of over voltage and under voltage and over frequency, under frequency. I'm not going to repeat that. You can see, for example, gradual insulation failure. You understand the damages it can cause to electronic devices. So I'm not going to repeat that. So all I'm saying is that these faults can be classified as overcurrent, over voltage, under voltage, over frequency, under frequency, and also power, reverse power, many different things, many different types we have got. This overcurrent as a result of short circuit, as a result of lightning, as a result of switching impulses. The effect, well, the damage, you can see. Sensitive electronic devices, especially the PC boards, the computer boards, the internet servers or something, well, they can easily be damaged. So the first option is fuse protection. It's normally against overcurrent faults. So that's the protection device like that. We have got different ratings. So what is the beauty about these fuses? As I said, it's a combination of protection and switching. So when you have got 1 amp fuse in here, it not only understands that this current that is passing here is a load current or a fault current. It not only understands that, but also, if required, it can switch open. It means it will chill itself. It makes a suicide. It will chill itself by blowing up, just to save your system. So it's a combination of switching and protection. That's the good thing about that. But the relay requires more than that. So what are the fuse applications? not very important loads, in very simple terms, like distribution loads, not transmission load. If I say that this line, can you see this line? Yes. For example, just as an example, if it's not line, for example, the feeder, okay, a 22 kV feeder, a 33 kV feeder, if it is feeding somewhere in the city of Oxford, if I'm saying you that I'm just going to make it fuse protected, you will laugh at me. Fuse protected, mate? This is supplying part of Oxford, yes, and you are making it fuse protected. Are you joking? It's not going to happen like that. So it's not a fuse application, even if I've got a fuse for that voltage range. It's not going to happen like that. So you must be very careful about if you lose that feeder, what would happen. You are going to save a lot of money by replacing the relay with fuse, so you have to be very, very careful about that. So benefits: cheap, fast operation, serves two purposes: fault detector and interrupter. However, limitations: can only detect overcurrent faults. Only one current time characteristic, needs replacement after operating. Used for LV and MV applications, max up to 66 kV. And again, not for main feeders. I can add to the limitations as we discussed, like exposed to aging, okay, affected by aging, dust, corrosion, humidity. So again, we have got this is small circuit breakers. So again, I'm talking about LV, low voltage. Again, this by itself is a combination of protection and switch. Switch or isolator or interrupted is a circuit breaker, okay? Who knows what is the protection side of that? There is no relay inside it. So what is inside this circuit breaker, in your opinion, that can protect the system? There is something inside this circuit breaker that can trip this circuit breaker. What is that? There is no relay inside it, but there is something else. I'm pretty sure you have studied that in the high school. Can you remember that? Do you remember the name of that system which used two different metal strips? Do you remember that? That they had different melting points? Yes, Alec, bimetal strip. Yes, that's what it is. So it's something like a combination of protection and switch. Bimetal strips. So you have got two strips, metal strips of different type. Therefore, they have been joined together, connected at one point. So when you have got high current, yes, these two metal strips tend to melt. As a result of that, the first thing that happens out of that heat is that they will try to bend down. But since they are of different materials, the bending between the two is not the same. The melting point is not the same. Yes, as a result of that, they try to bend. And that bending is enough for switching this circuit breaker. So they are miniature circuit breakers. And we have got a lot of them in the industry. So main purposes of the circuit breakers: switching loads, breaking fault current, and carrying through fault current safely. The specifications: the speed is important, therefore fault clearing time, and breaker rupturing capacity. So the idea for circuit breaker is to operate under load current and under fault current. You have got a lamp, you have got a light, yes, you have got a switch. There is no fault, there is no problem, but you should be able to turn on the light or turn off the light. So that's one purpose of the circuit breaker. At the same time, if there is a problem, if there is a short circuit, you need that circuit breaker to operate automatically, not you go and do it, automatically, and open under the fault. So these are the purposes of the circuit breaker: to operate manually under your discretion, under your command and control for load, and operate automatically under default. So this is what you would like to have. All I'm saying is that fault clearance time is important. So if someone asks you what is the fault clearance time, you would say, well, if you're talking about fuse operation, well, easy. The time it takes for the fuse to melt down, the fuse link. Yes, easy. What about relay protection? Well, according to the relay settings, once the fault occurs, first, it will take some time for the relay to operate. Okay, so can I say the fault is cleared? Nope. I said the relay is operated. So what will happen then? Well, what will happen is that a trip signal will be sent to someone else. And who is that someone else? Circuit breaker. Oh, okay. So can I say that as soon as the circuit breaker receives the trip signal from the relay, it will operate? No. So what will happen inside the circuit breaker? Well, that circuit breaker has got a trip coil. Okay, so when that current is received from the relay, that trip coil will be energized. Okay, so can I say that the circuit breaker will operate as soon as the trip coil is energized? Nope. Again, the circuit breaker contacts try to separate. Okay, so can I say at the time of separation, exactly at the time of separation, the circuit breaker is open and the fault is clear? No. So what? Well, still the arc is there. So it takes some time for the arc to move away, and it all depends on the insulation material and the distance of the two contacts of the circuit breaker. Oh, okay. So it takes some time for the operation of the circuit breaker. Yes. And it takes some time for the operation of the relay. Yes. So when you say the total fault clearance time, it is a combination of the relay operation plus the circuit breaker operation. Correct. And don't forget, the relay should be reset again, ready for the next operation. So that's how it is. Oh, okay. So that's where we can say now the system is clear, safe, and go and do operations. Yes, this is what I say by that. So you may have seen this kind of very, very old electromechanical relay. The basis of operation is based on what I told you before. I referred you back to Mr. Faraday. I referred you back to Mr. Fleming. You have got a coil. This coil, if you push a current into the coil, there will be an electromagnetic field around it. I can use this in two forms. If I have got that coil in here, yes, I can put a needle, a pointer in here, and I will put a scale in here, and I can use that electromagnetism of pushing a current in here and having electromagnetic fields around here in order to create a torque and to make the needle to move. This is what I said when I was talking to you in terms of metering, measuring. That's one application. So, well, I can use the same concept, but this time for protection, not for metering. Like what? Okay, so see this? Again, this relay has got exactly the same mechanism. It has got the permanent magnet. Yes. See that disc? Yes. Replace that disc with that pointer, with that needle. Okay, so that disc at the beginning is under the influence of N and S. Where is that N and S? Where is that? It's in here. Look, 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 look. See this? See the magnet or not? So it is in there. It is in between in there. It's been stopped. It's a braking torque. The relay Disk does not move. No fault. So what about if there's a fault? Aha! When there is a fault, we have got a coil, trip coil. Yes. So the current goes into the coil. Yes. So there will be an electromagnetic field. Yes. As a result of that, there will be a torque. Yes. This torque will oppose the torque of the permanent magnet. Yes. Aha. And if this torque is stronger than the torque of the permanent magnet, guess what? The disk will start to rotate. Okay, so under what situation I can say that the torque is enough to make the disk rotate? It goes back to the setting of the relay. You do it in a way so that even for a small bit of torque, it will start to move all. For a very strong torque, it will start to move. Okay, so is it current setting of the relay? Yes. Is it correct to say that another name for current setting is pickup setting of the relay? Yes. So where is that in the relay? Here. See this is what we call plug. You can take it out and put it in another hole. Hole. That's it. You just change the pickup setting of the relay. You just make it more and less sensitive. So, okay, so put it this way. When the relay disk starts to rotate, then what? See this shaft? Yes. Okay, this shaft will move. Okay, so previously this shaft was connected to a needle and we could have some reading for current. So it's not a meter, it's not a galvanometer, it's not an ammeter, it's a relay, it's a current relay. So what will happen? Okay, see these contacts, auxiliary contacts? Yes, when the disk starts to move, that shaft or gear will start to move. Yes. And those auxiliary contacts will change position from on to off or off to on. Yes, and that's enough to send a trip signal from a DC source, which happens to a battery, to a circuit breaker. By the way, what is on top of this relay, this bit? Yes, that's the time setting. Okay, so the time setting is on the top and the current setting is at the bottom, and you have got a disk which is under the influence of the torque, which is a combination of current setting and time setting. That's right. And when the disk starts to move, the auxiliary contacts change position. Correct. And out of that, a DC signal, a DC voltage that was hidden somewhere is now free to move away towards the circuit breaker trip coil. Yep. And the circuit breaker trip coil will be energized. Yes. And that is enough for activating a spring mechanism that is connected to the contacts of the circuit breaker. Yes. And that the spring mechanism will make the two contacts of the circuit breaker to get apart. And the circuit breaker is tripped and open. Yes, and guess what, my dear friends? This will bring me to the end of this presentation tonight, my time. And I hope you have enjoyed it with me. Thank you very much, everyone, for coming along and listening to me. If you have got any question, please ask. I'm sure that you will understand the rest of these pages. So I've already talked about the combination of relay and circuit breaker protection. I talked everything about the mechanism, the trip coil and the auxiliary contacts and the spring mechanism in here. So you have to read for yourself. I talked about everything regarding the relay protection that goes to relay, current protection, voltage protection, frequency protection, phase protection, and everything. I've already told you everything. I told you about the pickup setting and the time it takes actually for the relay to operate, okay? And I told you about the advantages and disadvantages of relay protection as opposed to fuse protection. I talked to you about the feeder protection. I talked to you about the strong faults and the weak faults and the operation to be quick. I talked to you about this magnet and the disk and these opposing torques and things that will create and how the disk will move in here. I told you about the good things about the electromechanical things and the bad things, and the operating times for the electromechanical relays that are bigger than these good relays, which are static relays or numerical relays. And these are the new technology that we have got in here, programmable and everything. Any questions? Are you happy with my performance? I hope you have enjoyed it and been happy with my performance. I tried my best to be as efficient as possible. Thank you very much, everyone, for coming along and listening to me. And if you have got any further issues, please communicate with the unit coordinator and help will be coming with you. Thanks, everyone, and hope to see you in another course with me. Thank you, UK, and good night.